let's start with the first session of the day, Emission Control Technology to Euro 7. The first section will be opened by Matthew Keenan from Ricardo, that we talk about Ricardo's sustainable roadmap to meet the Euro 7 regulation. Matthew, are you there?
Yes, good morning, Nancy. Thank you very much. I'm just going to share my screen and we can start the discussion. Can you see my screen okay?
Yes, perfectly, thanks.
Okay, perfect, thank you. Okay, so yeah, so this morning, I'll hopefully set the scene for what we at Ricardo think are going to be some of the important challenges in having very good emissions control in our transport sector. So the transport sector has been changing significantly over the previous few years, and we really try and see where the main catalytic challenges may lie in terms of different tailpipe species that need controlling, in terms of the temperature that these systems will need to operate at, and in terms of the impact of real world conditions on how the emissions control is still necessary, and how we can ensure that we have very low tailpipe emissions from our transport sector. So we've got 3 sections this morning. We'll have an introduction, just to have a look at some of the drivers really. So some of the European drivers that are impacting the automotive industry. We look at Euro 7 impacts. Later this year, the Commission should be publishing their first draft of Euro 7. So it'll be interesting to see how that fits. And then finally, we'll have some summaries on what we think about the future transport system may look like. So hopefully, as you all know, the EU has set its Green Deal, and it's really to give really pushing the boundaries for very strong climate ambitions. I've got 3 statements here which have been taken directly from the Commission's press release, and it's really quite interesting. So they've got the top one in bold: policies fit for reducing net greenhouse gases emissions by at least 55% by 2030 compared to 1990 levels. So this is a real significant challenge for many sectors, not just the transport sector, but it does have really specific impacts to the applications that we will be driving now and the applications that we'll be driving in 10, 15 years. So this Green Deal is really shaping some of the types of technologies that will be out there in the coming years. The second point is the Commission would like to have to be the first climate neutral continent by 2050. So real ambitious plans here to be carbon neutral. Interesting to understand how this might in fact impact renewable fuels, future fuels, non-carbon based fuels as well. So hopefully we can have a little discussion today around what types of fuels you might see moving forward. And finally at the bottom, which is a real immediate impact. So there's a real acceleration in reducing the emissions from passenger cars and also vans. So there's been emissions legislation that's been around for a while to reduce CO2 emissions, but now we have some extremely strong factors here where we're looking at 55% reduction in tailpipe CO2 from 2030 compared to 2021, and then 100% reduction from 2035 compared to 2021. So these 2 steps in CO2 control are really driving technology choices and really pushing the types of development that are occurring in the automotive industry. So let's just have a look where we've come from in terms of CO2 for the European fleet. So the chart on the left-hand side shows you the emissions in blue from passenger cars and in orange for vans in terms of grams per kilometre of CO2. And you can see from the year 2000, we had approximately 175 grams per kilometre CO2. And throughout the past 20 years or so, you can see we've had technology steps, significant introduction of diesel vehicles, which have all helped reducing the CO2 emissions. And the next target we have is this year. So the target for this year is meeting 95 grams per kilometre CO2 for the fleet average for passenger cars. And last year, we were at 108 grams per kilometre CO2. So we've got a step change from 108 down to 95. So we're talking a reduction of 13 grams per kilometre fleet average in CO2 from where we are to last year to where we need to be by the end of this year. So you can see it's quite a steep trajectory from where we were in 2019, where unfortunately the tailpipe CO2 emissions average had increased in the previous few years, but then over the last year or so, we've had a significant step change in these tailpipe CO2 emissions. So it's real challenging targets which are being set by the Commission. And then if you look at the right-hand side, you can see the historical targets. So 2015, we had 130 grams per kilometre. And then towards 2025, we are aiming towards 80 grams per kilometre. You get to 2030 with the 55% reduction, you're targeting in the region of 40 grams per kilometre. And then at 2035, we are targeting 0. So this is a kind of a looking back and looking forward. We've done a lot of technological advances to get to where we are today in terms of CO2 reduction, but now we need the next step in technology to help us achieve those very low levels at 2030 and also 0 at 2035. So what's happening? So you've obviously seen all the information in the newspapers, websites, etc., showing that there's a significant shift from the internal combustion engine to electric applications for many passenger cars. And here are just a few snapshots of announcements from many of the car makers showing their commitment to invest in battery electric vehicles in the time frame of 2030 for many of the manufacturers. And even prior to 2030 by some manufacturers. For example, Jaguar is saying that they plan to have an all-electric fleet by 2025. So this is quite a significant challenge and quite a significant change from where we have been historically. You know, we've had over 100 years of internal combustion engines, and now we are completely switching the propulsion technology. The chart on the top left gives us a look at the sales of vehicles in the UK from January to September in 2020 compared to the sales of vehicles this year from January to September. And what you can see is on the left-hand side where we have pure internal combustion engine, this is a mixture of both gasoline and diesel. So you can see there's a step change there from going from 1 year to the next year. So we're starting to see a dramatic reduction in pure internal combustion engines. And we're also seeing a significant increase in the battery electric vehicles. So in 2020, for the first 9 months of the year, approximately 5% of the fleet was battery electric. And this year, for the first 9 months, approximately 10% of the fleet is battery electric. So we're seeing the customer is open to these technologies. The customer is purchasing these technologies. And on the right-hand side, you can see the hybrid vehicles. So these are internal combustion engines with types of hybridization. So this can be, battery propulsion. It can be recuperating energy. It can be stop-start. There's a whole range of different hybrid technologies there. And you can see there's a step change there. So we are seeing significant increases in hybrid technology. So we're starting to see a shift from pure internal combustion engines to battery electric and hybrid applications. And this gives us some interesting challenges as we move forward. Similarly for trucks as well, there's significant CO2 legislation in place for trucks. So if we just look at the large Class 8 trucks, well, they are targeted with a 15% reduction in CO2 at 2025. dropping to a 30% reduction in CO2 at 2030. And these are all relative to the CO2 emissions at 2020. So you really need to have a good understanding of where you are now and how your trucks are behaving now, performing in terms of CO2 and fuel economy, etc. And then you have to have your walk of how you go from where you are today all the way down towards 2030 with significant CO2 reduction targets. And the CO2 reduction targets are following for different classes of trucks. So the whole arena is now significantly focusing at reducing CO2 from the tailpipe of the vehicles. Okay, and just to complement those CO2 requirements, we are starting to see some interesting technologies applying to the large application sector. So this is just one interesting application. And this application is being brought into service because of local legislation. So ultra-low emission zones that are occurring around Europe, around the globe, these are in some cases superseding what the Commission is looking at in terms of its global CO2 and global emissions legislation. So here in Brighton, we have a low emission zone. This is approximately a 2-kilometre zone through the city centre. It's a really historic, congested part of the city. Lots of taxis, lots of buses, and historically lots of passenger cars, but passenger cars can't follow all of this route anymore. So what we have here is we have the local bus company, which is purchasing hybrid technology for buses. And this is a technology where we have a Euro 6 internal combustion engine with all the after treatment technology, the diesel oxidation catalyst, the SCR system, the DPF, etc. So it's a really modern engine with very good emissions control. And that engine is purely charging the battery. And then the battery powers the electric motors that propel the bus. So the engine is not connected to the wheels. The engine is just generating electricity for the battery. And this is what happens outside of the low emission zone. The engine is on. The engine turns off when it stops at bus stops, but generally the engine's on continuously, charging up the batteries. And then when the application enters the low emission zone, it switches to pure electric mode, and it operates for approximately 2 kilometers in pure electric mode. So even some of the larger applications are having hybrid technology and also operating on pure electric mode, which is quite interesting, even in some of these large applications. Okay, so Euro 7 and beyond. So what does this mean for our passenger car technology? What does it mean for our truck technology? And what does it mean for some of our large engine technologies? So we'll have a quick walk through how we think this will impact technology. So Euro 7, not before 2025 from the Commission's view. And this is going to be the last emissions legislation. And it's therefore, because it's the last emissions legislation, it needs to incorporate current fuels and future fuels. So this will cross-cut all the different fuels we have now and any of the new fuels that we have in the future. And those new fuels could be hydrogen, they could be ammonia. And we'll come on to those a bit later on. So very differently to how we do our emissions testing at the moment and how we meet the tailpipe emissions limit, you normally drive a specific cycle, and that cycle has a fixed length, and you have to be able to control the emissions in that fixed length. That is changing at Euro 7 to allow any trip to be a valid trip, and you have to control your emissions in any trip. And so this allows us, for example, you have a budget of emissions, you are allowed to emit a certain amount of emissions up to a certain driving distance. And then once you exceed a certain driving distance, then you revert back to the more traditional milligrams per kilometre of your emission. So the top shot there shows you how this can be visualized. So for example, from distance 0 to distance 8 kilometers, you could have a budget. And then after that distance, you would revert to, for example, the orange line, which is 60 milligrams per kilometre, which is where we are today at Euro 6 for NOx emissions. Or you could have a budget for the first 16 kilometers. And then after the 16 kilometers in red, you could have a 30 milligram per kilometre limit for your NOx emissions. So this is what we're expecting to be discussed later this year when the Commission gives their first proposals. And this is in place to ensure we have very good emissions control under cold start, low speed driving, city driving, where we know after treatment can be challenged, where we know after treatment could be a bit cool and therefore not so efficient. So if we look at typical solutions, so what we might need is for a Euro 7 gasoline after treatment solution, because we need to control emissions in very challenging conditions, so cold conditions, cold start conditions, stop start conditions for the vehicle, then there's a push there to use an electrically heated catalyst. So we're electrically heating the catalyst system independent of the engine. So you could use your regenerative braking, you can use the energy stored in the battery to power your electrically heated catalyst. Then we'll have a very close coupled three-way catalyst, more of a traditional three-way catalyst that we're used to. We also need a gasoline particulate filter. So again, trapping particles is now a challenge for gasoline vehicles. Historically, it was always a diesel challenge. Now it's a gasoline challenge due to the limit that is being set for particle number. Probably a second three-way catalyst to control emissions under high speed, high flow. And finally, we might need to have an ammonia control catalyst as well. Ammonia will be controlled at Euro 7. And we all know operating a three-way catalyst slightly rich, so in slightly oxygen reduced conditions, we can transform NOx into ammonia. So we might need to have some kind of ammonia control catalyst. So this brings up a new complex system for Euro 7. There are multiple elements in the gasoline exhaust system, which traditionally we've just focused on three-way catalyst, and quite recently we've added a GPF. Now you're going to add in more control systems, which gives us more catalytic challenges. So I still think we have an interesting role to play moving forward in terms of catalysis and emissions control. And to try and optimize and synergize all these catalysts will be key moving forward. Okay, I just want to quickly move on to the heavy duty challenge. So again, we have this kind of area where we will have a budget after start of engine. So again, this allows us to control the emissions in a heavy duty application under all driving conditions, or under almost all driving conditions. So we're able to ensure that we have very good emissions control from effectively the start of the engine. So you can have a budget for operating for a certain distance or a certain power, and then after that time frame or distance or power, we'll switch to the more traditional milligrams per kilowatt hour. So again, this allows us for short tests, long tests. It removes previous weighting of hot and cold testing. So every operation, every driving operation needs to be valid, and the emissions in that cycle need to be well controlled. We're going to have additional pollutants to control, ammonia, N2O. And also, as I mentioned before, we will need to be able to meet all these limits and ambient conditions if we're using hydrogen as fuel or if we're using ammonia as a fuel. And I think that's quite interesting, the way the heavy duty arena is looking more seriously at hydrogen and ammonia. Okay. So if we look at what a heavy duty after treatment system might look like towards Euro 7, so this is 2025 and beyond. Because of the cold start challenge, because of the every trip being a valid trip where you need to control your emissions, then we are probably going to have a very close coupled SCR system. So traditionally in a truck, the after treatment system is 1 meters away or 2 meters away. It's in a box in a relatively cold position on the chassis of the vehicle. We're going to have to put a small SCR system very close to the turbocharger to use the heat from the engine to control the emissions. So we get this really complicated after treatment system where you have a urea injector, you have an SCR, an ammonia slip catalyst, which is quite small. So it is only really effective under limited cold start, low load operation. And then we have our more traditional DOC, DPF, SCR, ammonia slip catalyst. So it becomes a really complicated system. But what this does allow us, it allows us to reach very low tailpipe emissions. So the tailpipe emissions for this type of system, for a low load cycle or a delivery cycle, so these are challenging cycles, we're targeting, less than 70 milligrams per kilowatt hour for NOx emissions. So we can still meet the requirements with traditional technology. However, some of the challenges here is an SCR catalyst is not used to being in a hot position of the exhaust. So what does that mean for its thermal durability? What does that mean for poisoning? Is it going to be more readily poisoned because it's the first brick in the exhaust system? So these are some of the unknowns at the moment in terms of using close-coupled SCR and having these very complicated after-treatment systems. So, we might need to do research and to say, okay, so how do we make the close-coupled SCR, which is quite small, how do we make it more durable? How do we make it more resistant to poisons? So I think that's an interesting challenge which we still need to look at. So I mentioned before about hydrogen as a fuel. Heavy duty applications are seriously looking at a hydrogen internal combustion engine. And I guess a simple point for the hydrogen internal combustion engine is hydrogen burns really easily. And also the purity of the hydrogen isn't so important for an engine. The purity of hydrogen is really important for a fuel cell. We can burn anything in an engine. And that's one of the beauties about the infrastructure for a hydrogen ICE compared to a fuel cell infrastructure. And the top chart here shows you the Ricardo view. So if you look, we see that the blue expansion from 2026 towards 2030 for the hydrogen internal combustion engine. And then we see it expanding out towards 2040 and 2050. And this is quite interesting. So we do see continuation of internal combustion engines, just using different fuels. So we won't be using diesel anymore. We probably won't be using natural gas anymore. We'll be focusing more on hydrogen. However, the challenge with hydrogen, it still makes NOx in the combustion process. So you will still need to have exhaust NOx control. And because we're using an internal combustion engine, you will still get particles, and the particles generally will come from the lubricating oil. So you will still potentially need a particle filter. So again, even though we're moving to a carbon-free fuel, there's still emissions challenges which we need to understand. So we need to understand if we're using NOx control for a heavy-duty application, do we use hydrogen as the reductant, or do we use ammonia as the reductant, or do we use both? And we use the different reductants at different temperatures of operation for the catalyst. So I think this is a really interesting challenge here. What kind of after treatment system do we have for the hydrogen engine? And more importantly, what kind of reductant do we have? Keeping an eye on having low or no selectivity to N2O. We don't want to make any N2O from a hydrogen engine because this really will impact our greenhouse gas emissions for a carbon-free fuel. Okay, I'm slowly running out of time, so let me just jump to the ammonia engine. Okay, so the ammonia engine is being seriously investigated for marine applications. Studies are starting, demonstrator programs are starting as well. We have an international distribution of ammonia, so we know how to transport it. It's a liquid, we handle it regularly. We've got a large production of ammonia globally for fertilizers. So there's a potential here to use ammonia as a fuel in some of these very large engines. Challenges though, you burn ammonia, you will make NOx, you will have ammonia slip, and you can have N2O being formed. Therefore, you need an SCR catalyst to control the NOx. However, we do understand SCR catalysts at the moment, some of them can make N2O. Okay. So you could get yourself into a situation where after your SCR catalyst, you have low NOx, you have potentially high ammonia, and you have some N2O. So we're going to need an ammonia slip catalyst to control the ammonia. We also know that ammonia slip catalysts can form N2O as well. So you could end up having an ammonia engine, which is carbon-free fuel, but having quite a big greenhouse gas footprint because of the N2O that's being formed. So the biggest challenge, I think, for the ammonia engine is really eliminating N2O formation. So can we optimize the combustion to minimize N2O? Yeah, that's our job, and that's what we will be aiming to do. Can we have SCR catalysts, for example, like vanadium or other technologies that can give us very low N2O? And then finally, can we develop ammonia slip catalysts where the selectivity is very high to nitrogen and the selectivity is very low to N2O? And I think that's where the challenge will lie in terms of after treatment for the ammonia engine. So we're seeing a shift to different types of fuels. However, even these new fuels, which are carbon-free, do have significant emissions control challenges. And I think it's the community that we're in today, and we will be the people who will be developing these solutions in order to have good technology steps where we can have zero CO2, but also extremely low emissions from the engines in terms of nitrogen species or particles, etc. So I'm aware that I'm probably just up on time. So I guess in summary, there are catalytic challenges in passenger cars still. Gasoline applications will still need a whole suite of catalysts. Heavy duty applications, again, a whole suite of catalysts are being developed and implemented for diesel. New catalyst systems will need to be developed for hydrogen internal combustion engines. And also for the ammonia engine, selectivity is going to be key in order to minimize any of greenhouse gas emissions. Okay, I think I'll stop there and open up to any questions.
Thank you, Matthew. As usual, was like a really comprehensive talk to open our workshop, and you put on the table a few topics that we are going then to investigate better with the specific talk on later on in the session. So maybe we can move to introduce the other speaker of the session, and then we can leave the question at the end.
Fine, yes.
Thank you, Matthew. So I would like to invite to this virtual stage Jose Maria Herreros from the University of Birmingham.
Thank you, Nancy.
And today is going to present a contribution from the synergy between hydrogen and exhaust after treatment system. So perfectly on topic for what we have just listened from Matthew Keenan.
So I'm sharing my screen now.
Yes.
Can you see my screen now? Yeah.
Perfect. Thank you so much.
Thank you. So yes, as Nancy mentioned before, my name is Jose Martin Herreros from the University of Birmingham. And the talk today is about synergies between hydrogen and exhaust after treatment system for emission control. We're going to present here some of the work that we have been doing in the last perhaps 7-8 years at the Future Power System Group with my colleagues, Professor Thanos Solakis, Dr. Sohesa Teresai, and myself, Martin Herreros. So we have divided the presentation in 3 main sections. The first of one, very briefly about ourselves, University of Birmingham, and our group. Also, we will define briefly, but Matthew has done in an excellent way, the problem statement, challenges that we are having with emissions, and perhaps see which solutions we could have to tackle those challenges. And then it should take the major part of the time if we will present some case studies that we have done based on the interaction between hydrogen in engines and hydrogens with the after treatment system, majorly applied to combustion ignition engines, DOC and hydrocarbon SCR, as well as to spark ignition engines. So to start with, we belong to the University of Birmingham, that is composed of 5 academic colleges, 26 schools, and 9 institutes. We belong to the College of Engineering and Physical Sciences, to the School of Engineering, that is composed of around 100 academics, 75 research fellows, and a student population of more than 2,000 students. We have just been allocated, let's say, in our new building that it has been opened this year. And in fact, a couple of years ago was the open ceremony of the official open ceremony of the building. And then within the School of Engineering, we have the Vehicle Technology Research Group, Research Center, and in our case, the Future Power System Group. So within the group, we have been doing some research in areas including zero carbon energy carriers, particularly hydrogen and ammonia. We have been investigating hydrogen and ammonia in dual fuel engines, mainly in diesel engines, as going after treatment system. We also have done some research on cryogenic engine, in that case a liquefied nitrogen engine. We saw a picture later on alternative fuels in terms of characterization, properties, and how the fuels later on burned in the engine. Waste heat recovery and fuel reforming, combustion and emission control, gaseous and particle emission speciation, and particular in terms of after treatment system, after treatment architecture, design, and thermal management. And then one of the examples of our contribution was in the Horizon 2020 project with title Partial PGM, involving multiple partners from Europe and the United States, and one of the leading partners was Johnson Matthey. So in our group, we have a series of facilities. I have put just FTIR to measure gaseous emissions, and I put here the picture of an equipment that we use to measure hydrogen in real time. So the equipment is able to measure hydrogen around 20 records per second, but we usually use the equipment in the mode of 10 or 1 measurements per second. So in terms of the problem statement, and don't repeat in much what Matthew already explained, I have included here a picture on how the European regulation has evolved from Euro 3 to Euro 6D. On the top one for diesel vehicles, and on the bottom one for gasoline cars. For each regulation, we can see 2 clouds. The outer cloud is the real values, that have been measured on road measured values, and in the inside, the regulated value. So this was very famous some years ago, the discrepancy that we had between the regulated value and the real values, particularly in the case of diesel engines. And interestingly, we can see how the Euro 6B and Euro 6D regulation has made it possible to reduce also the real NOx value, and we are getting closer the real value to the regulated value. So now, as we mentioned before, in 2021, we are going to have coming the Euro 7. There are some drafts already there, so we will have more stringent emission limits. In terms of particles, we will go perhaps for not only to measure particles above 23 nanometers, but also particles above 10 nanometers. We will have more species to be regulated, like in the case of N2O and the case of ammonia. So I have just identified here some of the examples of the challenges that industry and ourselves have been facing in terms of diesel, for example, and we still are facing there, how to improve cold start, how to improve transient emissions or emission at high load. In terms of the after treatment system, if we need any reductants to increase the effectiveness of the treatment system, if we can generate the reductant ourselves on board. And when we have, for example, a particle filter and we need to regenerate a particle filter, trying to improve how efficiently we regenerate the particle filter. And in the case of gas injection engine, very typical example, challenges to improve simultaneously fuel economy as well as to reduce emissions. For example, we can try to run the engine in lean operation to improve fuel economy, but then at the same time we will be troubled the three-way catalyst to perform well because we will have excess of oxygen in the exhaust, and then we might need other type of catalyst also here. So far, we have been working with those challenges to try to fulfill those emission regulations, and now, if other type of pollutants are regulated, we will still need to keep working on these challenges, but targeting perhaps now these particles emission, small particles emission between 10 to 20 nanometers, N2O, and ammonia, and how the measures that we have made before are affecting now to also ammonia and N2O. So we believe that this after treatment system can help also to Euro 7. Some of the measures that we could investigate is engine control optimization, the use of electrical heating strategies, particularly now that if we have hybrid vehicles or we have batteries inside on board the vehicle, that we will be able to have electrical heated catalysts independently of the engine, or the use of phase change materials. See how we should structure or how will be the architecture of the after treatment system, and Matthew mentioned before, particularly for the case of combustion engine engine, will be a bit complex, the system, so how we can optimize that. Perhaps try to understand how the after treatment system work with different fuels, and when we talk about different fuels, we mention liquid fuel, gaseous fuel, including hydrogen and ammonia, and then linking with advanced fuels. Try to understand what will be the effect of those fuels, for example, here hydrogen or ammonia on the exhaust after treatment system. And if we are going to use hydrogen in our engine, how we are going to obtain this hydrogen. Also, in the past at the university, we have been working trying to produce this hydrogen on board. So in the exhaust system, we have wasted CO2, wasted water, wasted heat. So try to use all this waste component to transform our fuel to, in that case, hydrogen and CO that could be recirculated back to the engine intake, or could be used on the after treatment system to see the effect that is having on them. And again, talking about fuels, and if our target is hydrogen, we could be working with gasoline, butanol, ethanol, all of them has hydrogen in the fuel molecule, as well as ammonia, that has a very high proportion of hydrogen in terms of mass in the fuel molecule. And then going a bit more in depth on the case study that we have been investigated. The first one, I have prepared an schematic here, and we will have in this case a diesel engine, and then we are trying to investigate how much is what is the effect of hydrogen being injected upstream on, in this case, a diesel oxidation catalyst. Then we have done the test with a small catalyst inside a reactor, inside a furnace, because this allows us to study independently residence times through the catalyst, temperature, the catalyst, and species concentration after in the catalyst independently of the engine operation. Then by doing that, we observe how and when we did the catalyst light off without hydrogen, the catalyst started to be active around 130 degrees. And then when we were injecting this upstream hydrogen, we were able to make the catalyst active at lower temperatures. Something interesting here was that there were small hydrogen of additions were able to enhance catalyst activity, but we were keeping our increasing the hydrogen concentration, and then the advantages were not so great. So it seems that we have some limitation here. And then doing further calculation afterwards, we understood that this is a combination of both. As a thermal effect, hydrogen is burned and this locally heat up the catalyst active site, as well as a chemical effect on hydrogen or hydrogen-derived species in the oxidation reaction. Similar type of setup using this mini catalyst, but in this case, we are using synthetic hydrogen from compressed hydrogen from a bottle. And let's try to understand how this synthetic hydrogen will affect the performance of a hydrocarbon SCR. Hydrocarbon SCR is a type of SCR that instead of using ammonia is using hydrocarbons to reduce NOx. We have also the option to use hydrogen SCR that is using hydrogen as a reductant. So then for this particular case, hydrocarbon SCR also needs hydrocarbon. So what we were doing here is an engine that allows us to use post-injection. So we were injecting our fuel very late in the expansion stroke of the engine. So the hydrocarbons were unburned, only partially burned, and then made available coming here for our SCR. So our SCR was fed by NOx, hydrogen, and hydrocarbon. So originally we saw at this temperature range around 180, 190 degrees that the catalyst activity was not very high when it was fed only by hydrocarbon. However, when we start to inject hydrogen, our catalyst activity was increased. And of course, we could have played here trying to optimize the process between how much hydrogen we can add and how much would be the hydrocarbon NOx ratio to try to make the catalyst as efficient as possible. In these lines, a very similar test that we also did, but in this case, instead to use the hydrocarbon remaining from the combustion chamber, we were trying to understand what is the impact of other type of hydrocarbons. So we were injecting pre-hydrocarbon SCR, butanol, GTL, and mixture of GTL, gas to liquid fuel, synthetic fuel, with butanol, simultaneously to hydrogen. And then we observed that by injecting butanol and hydrogen, we were able to obtain very high, close to 90% conversion efficiency in a relatively wide temperature range. What means that the fuel, or very active fuel, can help to hydrogen and to make our hydrocarbon SCR system more efficient. So the fuel is also playing a role here. And now again, on the topic of hydrocarbon SCR, but in this case, not so much focus on the hydrocarbon side and not injecting now hydrogen from a bottle. Now what we were doing, we were injecting ammonia. Then we were catalytically cracking, decomposing this ammonia into hydrogen and ammonia. Then depending on the condition here, we were having different proportions between hydrogen and unconverted ammonia. Then when we did was recirculated back this hydrogen and ammonia to our engine. Then we were able to replace some of the diesel fuel. This brought some advantages in terms of CO2 emissions. Depending on the composition of this mixture on hydrogen and ammonia, we observed that we are able to have a higher proportion of hydrogen, the mixture burns better, and we are able to obtain further reduction in CO2. But also what we did is take this hydrogen and ammonia mixture pre the SCR and try to see how effective it will be to our SCR catalyst. And then what we obtained was that from a very low initial conversion efficiency, again at a temperature range around 200, 220 degrees, then the conversion efficiency without the hydrogen and ammonia mixture was around 15–20%. Then by injecting hydrogen and ammonia, we were able to increase the effectiveness up to 60–65%. And by playing a little bit with the engine, and then we were using external recirculation, we were able to increase the NO2 to NOx ratio per SCR, and then to increase the conversion efficiency of our SCR close to 90%. So this was everything about compression ignition engine, and now let's move to the case of a spark ignition engine. I have to say that for the case of a spark ignition engine, our research has not been so much focused on the effect of hydrogen after treatment system, but more on how to produce this hydrogen. So at the university, we had an engine coupled with from a research project from a three-way catalyst followed by tire reformers. First, we tried to explore in our engine how much were the temperature that could arrive in the exhaust to see if the temperature would be enough or not to drive the endothermic reactions. And then we could see how taking a plate of the catalyst without reforming, the temperature was around 750 degrees. Then we injected a fuel, and then the temperature suddenly reduced to around 600 degrees. This means that we are able to use or to recover some waste heat from our engine. So that means that we are able to drive the endothermic reaction to produce hydrogen. When we did, we recirculated back this hydrogen and CO to the engine, and then we were able to improve the indicated efficiency of the engine, depending on the engine condition, up to 9%. We were able also to reduce NOx emissions. Again, these numbers here represent how much represent the reduction. So 0.06 means that we were able to reduce 94% NOx emission, 0.12 that we were able to reduce 88% NOx emission, as well as also we obtained reduction in the particles emission levels. And then to finish today, again with the topic of spark ignition engines, we did some preliminary work on the case of ammonia. And then we will study how is the dissociation of the cracking process of ammonia by using the exhaust of a gasoline direct injection engine. Then what we obtained is that we were able to recover some waste heat. Efficiency here higher than 100% in the way that we define it means that we are able to recover waste heat from the exhaust. We were able also, depending on temperature, to convert less or more successfully the ammonia to hydrogen. So when we increase temperature, we were able to increase the conversion to hydrogen. And then by doing some further calculations, we were able to predict how much energy we could recover from the engine and how much would be the impact in terms of CO2. This has to still be demonstrated by testing in a full-size cracker, let's say, to see if the predictions are correct or not. So what were we working now? What we're working now is try to understand the effects of hydrogen and perhaps reforming or partial product from ammonia cracking, or on the case of gasoline exhaust after treatment system. We are trying to improve the compactness of the exhaust after treatment system, including the hydrogen generation and utilization. And we are also trying to focus on what is the impact of hydrogen, of ammonia in terms of engine output, so in terms of emission production in the engine, as well as in terms of tailpipe emissions, or what is the impact of ammonia and N2O after the catalyst. So just to say, this is a work that has been done with multiple researchers at the University of Birmingham, as well as thank you very much to Johnson Matthey for providing the catalyst during the year to do this research. And that's the end of the presentation, and I will be happy to discuss or to reply any questions in the discussion session later.
Thank you, Jose, for the really interesting talk. And I'm sure there will be like plenty of questions in the discussion later. So now we can move to the last speaker of the session, that is Donato De Carolis, that will talk on the other topic that we have seen in Matthew opening, that is about the ammonia. So Donato De Carolis from Cardiff will present a study of spatial dynamic nature of catalysts during ammonia selective oxidation. Yes, I can see that. Perfect.
Can you see my screen?
Yes, perfectly. Thanks, Donato.
Hi everyone. I'm Donato. I'm a postdoc for the Catalysis Hub. I've been working on studying the selective ammonia oxidation on palladium and alumina catalysts, but in particular studying how the catalysts behave under reaction condition using spatial resolve method. Why will we want to use spatial resolve method? Well, when you use simple single spot analysis, you may start to form an idea of what your activity relationship is, but these may be highly dependent on where you're observing. Here, for example, you observe the center has a completely different behavior than if you look at the start of the catalyst or if you look at the end of the catalyst. And these may have a strong effect on the structure activity relationship we are trying to form, we're trying to understand, and how the catalysts behave, because as you know, there may be a temperature gradient as well as a gas concentration gradient across the bed, and this makes the analysis not as straightforward. As you can see here, for example, for CO oxidation, as the different, although 250 and 300 degrees look exactly the same to a normal user will look just at the end pipe measurement. If you look at the concentration of the gases at the various position, the conversion in this case, at various position, you see that 300 degrees you go 100% conversion pretty much already at 3 millimeter in, whereas 250 you only get it toward the end, which will make the analysis fallacious. For this reason, QB has developed a system called SPACI-FB. The SPACI-FB is a technique which allows direct measurement of any gas composition at various points across the bed, and combining this technique with spectroscopic other spectroscopic technique, for example, ZAFs, allow us to have a direct correlation between the structure and the activity at various points across the bed. This technique uses a capillary which has been bored through lasers, and this capillary is embedded through the catalyst bed. And rather than moving the capillary, because it's very fragile, we move the catalyst bed and we collect the capillary is connected to a mass spectrometer at the end, where the mass spectrometry data are collected. We apply this technique to ammonia oxidation. Why ammonia oxidation? Well, ammonia is a pollutant and a greenhouse gases, and is often used in the selective catalytic reduction of NOx. However, unreacted ammonia for NOx from this reaction may start to spill and pollute the environment. Therefore, a way to remove it is to apply a selective catalytic oxidation of this ammonia. So far, palladium and alumina are shown to be the most favorable in terms of selectivity and activity performance. It was found in previous paper that under reaction condition, palladium nitride is formed and is thought to be the selective phase. This palladium nitride phase is a hetero atom insertion on the palladium lattice, similar to what palladium hydride or palladium carbide is, and it was the first time which was found during this reaction. However, spatial resolve measurement will provide information about what is the true active phase for the system. We perform ZAFS analysis on the catalyst after reaction in hydrogen, you can see on A, and this is consistent with nanoparticulate palladium. However, after the introduction of reaction mixture at 100 degrees, you can see on B, a predominant interstitial palladium nitride phase is formed, and is uniformly formed across the bed, as evidenced by the shift of the multiple scattering peak at 24,319 and 24,420. As we increase the term, to enhance the information obtainable, from the Zanes, we applied multivariate curve resolution, which allow to obtain the discrete component of the spectra. The MCR method is particularly powerful in separating and identifying the evolving species within a large data set. We were able to find particular three spectral component to the Zane spectrum we found. One which can be ascertained to palladium oxide, one to palladium metal, and the other to palladium nitride. When applied this analysis to the Zane's data I showed you before, it's clear that the palladium nitride is the majority phase. However, it's possible to identify minor amount of both palladium oxide and palladium metal. Again, this proportion is consistent across the bed. However, as we increase the temperature to 175 degrees, which is prior to full conversion of ammonia, there's a clear spatial variance on the palladium speciation across the bed, as evident by both the Zane's MCR and the X-axis, so you can see in A and B, along with the spatial variation in the conversion of ammonia, C. From 3 millimeter onward, it's possible to see the consistent palladium nitrogen coordination number are indicative of partial oxidation, and after the bulk nitride is disrupted, although the MCR shows a consistent amount of palladium nitride still present in the system. These structural changes, these change between palladium metal, palladium nitride species, but still with the presence of palladium nitride present in the MCR, suggests that some structural change is happening, and we attributed it to a change. We attributed it to a change in where the nitrogen sit. Rather than sitting in the lattice position, now the nitrogen moves toward the surface of the catalyst, similar to what happened with palladium boride. And at this point, we think is what actually makes the catalyst selective toward nitrogen, active and selective toward nitrogen. In fact, as we increase the temperature to 300 degrees, higher oxidation product appear until at the inlet, the system is still predominantly palladium nitride. However, as we move forward, the amount of palladium nitride concentration drops dramatically, and therefore we start to see a higher amount of palladium of NOx being produced. So it is clear that there is a correlation between the amount of palladium nitride and the amount of nitrogen produced and the selectivity toward nitrogen, which is further exemplified when we increase the temperature to 400 degrees. Palladium nitride is pretty much disappear at this temperature, and it's only palladium oxide as a species, and this species is completely unselective toward nitrogen, and all the species N2O and NO appears as we increase the temperature. However, this finding poses an important question: why does the level of NO rises and fall across the length of the catalyst bed? Well, there could be another set of reaction taking place once the palladium nitride phase is removed. A reaction where NO and ammonia combine to produce N2O and with a first, which is basically an SCR-like behavior. This reaction has already been studied on palladium nanoparticle using hydrogen and methane, as previously shown by the previous talk. And we suggest that this change of phase, which happens after position 4, where you can see palladium nitride completely disappear, although you still have a small amount, caused the completely loss of selectivity of the system. So in general, we can see that as we change position across the bed, we have a much wider variance. In particular, we see that during the temperature series for the inlet of the reactor, the palladium speciation is predominant palladium nitride. However, as the reaction extern progresses toward the outlet, the bulk interstitial nitrogen become mobile. The MCR analysis identify a natural phase present. Even though palladium distance indicate is absent from the bulk of the particle, we suggest the presence of a surface natural structure. And while still nitrogen is present, there is still appreciable selectivity toward nitrogen. As the particle becomes more oxidized, there is a change of selectivity toward NOx product. And at 400 degrees in particular, that is a suggestion of not only ammonia selective catalytic oxidation is happening, but also selective catalytic reduction. I would like to thank everyone who collaborated with me, people from QB, Southampton, well, of course, Cardiff and Catalysis Hub, and the people from the various universities. Thank you very much for listening.
Thank you so much, Donato, for your contribution. I kindly invite all the speakers for the first session to put on the camera. So Matthew Keenan, Jose Herreros, and you, Donato. So we can start the session with the question.
Yeah.
I can see also that we have on camera Francisco, one the organizer of the UKEM meeting with me. And I think that is also Vangelis connected. So I don't see any question in the chat for the previous three talks. So I invite all the participants, if you have any question for Matthew, Jose, or Donato, just to open your mic and ask the question to our speaker.
Sorry, I have a question. Maybe I can start. And this question is for Jose Martin. Martin, I have a question. Is when you show us that you are using hydrogen for, let's say, to enhance the conversion, the activity of this catalyst, and when I was looking at this work, is this because you are thinking that in the future cars can have as well a small hydrogen cylinder to do this activation? Is this what are you thinking? Is this the idea behind, or I don't know? Tell us a little bit more about this.
Yes. Well, I think that for passenger cars, there is a big drive for electric. So I think that for passenger cars, most likely will be electric. For heavy duty or for marine or for this type of technology where electric are a bit more challenging, as Matthew also mentioned before, perhaps hydrogen, perhaps ammonia is a way forward, no? And hydrogen, I think one of the challenges of hydrogen is in terms of volume. It takes a big volume, no, of hydrogen, so it's quite difficult. No? Having one of the challenges. You could liquefy, you could compress, or you could store it in any other way. So we were trying to produce hydrogen on board and try to understand how this could facilitate the incorporation of hydrogen and then use for after treatment system. So in our case, in terms of research, we thought, okay, let's split that in part and let's try to understand first what is the effect of hydrogen on the after treatment system. If the effect of hydrogen is successful, okay, there is a point to going forward. But if the effect of hydrogen is not successful, okay, we know that there is no point to go forward. All these tests belong to an innovative UK and EPSRC project that the whole idea of the project was both generation of hydrogen on board and use of hydrogen. Now, one alternative could be that we have ammonia, no? So that's the reason that we are now trying to understand how ammonia can be decomposed to hydrogen, nitrogen, and converted ammonia. And then now we need to study not only what is the effect of hydrogen, but also the effect of hydrogen with some concentration of ammonia. So if the cars are going to have cylinders there of the trucks or the vans, maybe this is one of the options. Other option is maybe to use ammonia to do like a hydrogen storage, because ammonia can be also burned in engines. So I think that it could be multiple options there, but I think not for passenger cars.
Okay, perfect. Thank you so much.
Thank you, Jose. I think that a really good point is that, all the challenge that has been presented in this first section show how this problem needs to be tackled on different scales. So we need to have again, understanding at really a macroscopic level, then if we want to really achieve something that is an advancement in the technology. There is another question that, another point that has brought to the discussion from Tom Surgeon in the chat. So I read the message for you all, guys. So thanks all for a very interesting talk. Perhaps a naive question, but to what extent can oxygen enrichment of the air intake reduce polluting emission? Jose shared some data which touch on this, but I will be interested in all the speaker thoughts on the topic.
Shall I start and give my view from the engine point?
Thank you, Matthew.
Okay, yeah, so oxygen enrichment in the intake or lean combustion certainly has a significant impact on the emissions of carbon monoxide and hydrocarbons because of the excess oxygen. It also can, depending on how much excess oxygen you have, can reduce the engine out NOx emissions. So it does help in controlling engine out emissions. But once you have oxygen in the exhaust system, it gives you challenges in controlling your NOx emissions, requiring additional reductant into the exhaust.
Thank you, Matthew. Jose or Donato, you'd like to add something?
Yes, okay.
Sorry. No, please go ahead.
Yes, no, I mean, in the same line that Matthew, just perhaps only to add that oxygen enrichment could help also to reduce particles, to reduce soot, but it's not as effective as if you have we have demonstrated, or we have studied in the past that it's not as effective as having oxygen in the fuel. Having oxygen in the fuel there when you need the oxygen to inhibit soot formation was very effective. Putting oxygen in the intake could help, but not as much. But I think, as Matthew mentioned, the most important will be what is the impact in terms of the treatment system. We know that for a fuel catalyst is horrible. For in case of diesel combustion ignition engines, in the case that you are using very high rates of EGR and maybe you have deficit of oxygen there, it might be helpful. But yeah, I think it's a bit more challenging. Yeah.
I just wanted to say for ammonia oxidation, it is likely the higher amount of oxygen will negatively impact the reaction, because as you have seen from the talk, as you go from a more oxidized palladium, you have less selective ammonia selective catalytic oxidation. So possibly a lower amount of oxygen will improve the system by less eruption of the palladium nitrate system.
Yes, thanks, Donato. Do we have any other question from the audience? Another one from Fran.
I have another question. This is for Matthew. Matthew, thank you very much. I always love to see your talks because they give us a super nice starting point, an overview of what's going on. I was very curious about the last slide when you were mentioning this ammonia as a fuel, especially for engines in boats. I have a question about I know that the amount of NOx that you are producing if you are using ammonia as a fuel is going to be much higher than the ones that you are producing in diesel engines. But do you have an order of magnitude? I mean, it's how big are they?
I think to answer that question, Francisco, it's probably a little bit immature in the technology to give some hard numbers or factors compared to diesel. So it's a really immature technology, ammonia combustion. And yes, we are seeing relatively high ammonia emissions and relatively high NOx emissions. But as we move and mature the technology, my view would be that the NOx emissions would be similar to diesel or possibly slightly lower. I think the development of the engine, the injection system, the combustion will not necessarily make it worse than diesel, but we're at an early stage at the moment.
Okay, perfect. Thank you so much.
Or maybe what will change is the different contribution of these NOx. So we can say the speciation of these NOx, I think, for the different temperature in which you work.
Yeah, absolutely. The cooler the combustion, the tendency to have higher NO2, which can be positive for the after treatment system. But yes, again, specific combustion conditions and specific engine installations will have its own characteristics of emissions, which we look forward to understanding better.
Thank you, Matthew. Do we have any other question?
I just have, like, following up this question, I have one for Donato, because Donato, I think that this your research links pretty much with ammonia engines as well, and with NOx emissions, because that a tail of ammonia that you are treating is coming because of the after treatment before of the SCR. When you are doing your experiments, I can see that you are using palladium and you have a very interesting phase. You are producing that nitrate phase that is very active. I love to see that thing, to be honest. But my question is a bit more fundamental. When you are doing your experiments, which is the assumption that you have in the tail of ammonia? How much ammonia are you?
We're working with fairly high amount of ammonia. It was 0.5% of ammonia and 2% oxygen, so fairly high compared to other paper in the field, which usually use hundreds of ppms. We went for 0.5% of total gases of ammonia, so it was pretty high. So
okay, my understanding is like this ammonia pretty much is like is about like how good or bad we can control the injection of ammonia in the SCR, right?
Well, yes, of course. The amount of ammonia spills depends on, well, on the SCR capability, because the SCR the catalyst may behave worse with temperature. There are a series of conditions which can increase or reduce the amount of ammonia spilled. But we decided to go for this amount, this fairly high amount, because we wanted to reflect what's the worst condition, in a sense. What could be the worst case scenario, one of the worst case scenario.
Perfect. Yeah, that's very good. Very nice work, actually.
I have a question for Donato as well.
Please, Matthew, go ahead.
Thank you. I really like the spatial experiments, and you're seeing the evolution of NOx and N2O along the bed length. Hopefully it came out from my talk about N2O being a future challenge. I guess it's kind of an open question. Do you have any views on either minimizing the N2O formation, or do you have any views on how, using your techniques, you can investigate how we can remove the N2O from the systems?
That's a very difficult question to answer, because N2O appears to be a byproduct of the higher temperature. There is a correlation between higher temperature and N2O production. So if we can see that up to 175 degrees, around 200 degrees, the system is not prone to N2O formation, but as we increase the temperature, is more and more likely to be produced. Just to be clear, this experiment has been done in a steady state type of system. So the system, although it's not like an aging experiment, it has been left running for at least 20 to 30 minutes before even collecting the data. So it is quite stable at those temperatures. So the idea will be to reduce the amount of N2O to reduce the temperature of this reaction or improve the catalyst, which can be further studied. If we find an improvement for this catalyst, maybe a co-catalyst, which may be able to abate further the amount of N2O produced, we may study it spatially again and start to find at which point across the bed N2O is produced. So we may do shorter bed or change the spatial space velocity of the gases, try to play with all the parameters in order to improve our knowledge of this system, because there are so many parameters in catalysis you can play with to find what you want.
Yeah, it sounds like a very interesting challenge, doesn't it? So, if you can have high ammonia conversion at 300 degrees C and very low selectivity to N2O at that temperature, that sounds very appropriate.
Yeah, indeed. Well, when the experiment we did in the lab, we found that possibly the best spot will be around 200, 220 degrees, where you have minimal selectivity to N2O and highest selectivity toward nitrogen. There is still a minimal amount at those temperatures, whereas 175 we could see none, but we're not a full conversion. We're about 70% conversion, 175 degrees.
Okay, thank you for that.
Thank you so much for all your questions. I asked the audience if there is any new question. I can see no further question in the chat. Last chance for question.
Donato, I have another question. This is again about the experimental. So the reactor, the type of reactor that you're using, is it a packed bed reactor or you're using a monolith type reactor?
No, it's a powder reactor. It was powder. In theory, the SPASI technique has been developed also for monolith type of reactor. But in our case, since we were working with ZAFs, X-ray absorption spectroscopy, we needed to go for powder in order to allow to obtain relevant data.
Okay, yeah. I mean, my understanding is that this technique has been used before, like for the monoliths, but the data you saw as well is coming, I think, from Diamond, right?
The one I did was in PSI, Paul Schaffer Institute, the Super ZAS beamline in Switzerland.
Ah, okay, Switzerland. Okay, so I wanted to see if we are able to see this in synchrotrons as well, but perfect.
Yes, let's say that there is no this combined technique with EXAS for like a bigger scale. In Queens, Alex Goguet has this SPACI setup in which you can study monolith, so you can do the speciation of temperature and concentration for part of like a core monolith of like 1 inch, 1.5 inches, and the same you can do with DPF. So you can do that also if you have the channels that are close on the other side. They definitely are like a really useful technique if you need to understand or getting understanding of problem like the aging of the catalyst, poisoning of the catalyst along the catalytic bed, with where the catalyst is seeing different concentration of the exhaust. So definitely is like a powerful technique. Thank you so much. Then I think we can close the session, the first session of the morning. We are going to reconvene here at noon. So I would like to thank all the speakers for the first session. It was a really great start, and see you at 12. Thank you.
All right.
The second session for the UKEM. So thanks, Josie, for restarting the recording. The second session has Chair Vangelis that will chair the session, and is about the road to decarbonization. So I will leave the word to Vangelis that will introduce the first speaker for this session. Thanks, Vangelis.
Yes, thanks very much. So the first speaker is Professor Stuart James, and she will be presenting about porous liquids. So I'm really eager to hear about how a liquid can be porous as well. So Stuart, the floor is yours.
Thank you very much, Evangelos. So I'm going to try. Am I sharing already? Is that right?
Yes, you do. Yes.
Okay, so if I just go to,
but not in presentation mode. So please put that in presentation mode. Yeah.
Are we good?
Perfect.
Okay.
Yeah.
And can you see me as well?
Yes,
yes, we can. Yes.
Okay, great. So, well, thank you very much for the invitation to talk. It's always nice to talk at different meetings and see a whole bunch of different faces. Unfortunately, I can only see 2 or 3. But Also very nice to see Nancy in her new environment. We are missing her and her coffee, I have to say, over here in Belfast. So I'm going to talk about porous liquids, and I'm really delighted when people say, "Oh, that sounds weird and a bit intriguing," because it's something that's very counterintuitive. But what I'm going to try and get across to you is I think this is a very powerful new concept. Let me sort of try and sort of paint a picture. This came from a chance meeting with a chemical engineer who you may know, David Rooney, here in a corridor. And he said, you know, he knew that we worked on porous solids, MOFs and the like. And he said something which was really striking. And he said, you know, these porous solids, they're fantastically useful. They have high selectivity for different guests. He said, the problem is, from an engineering point of view, you can't pump them through pipes. And it was that sort of key sort of observation that started a little conversation, and we thought, oh, okay, so how do you do that then? Do you take these solids and do you have to mix them up and make a slurry or something like that? And could you but then pump those through pipes, and would that actually work? But a little bit later on, I realized there's actually a bigger concept here. It's not just about getting solids to flow through pipes. It's about porosity in the fluid state. So it's a broader thing, and this is what we call porous liquids. So I'm going to talk a little bit about the background, a couple of ideas, and hopefully leave myself enough time just to talk about the potential for CO2 capture. So again, going back a little bit in time, before we did this, I thought this, before we actually managed to prove it, I thought this was such an interesting idea. I wanted to write a paper about it, just as the idea. And so I published this, what's called a concept article back in 2007. I have to say, looking back on it, this is possibly the most important paper of my career, because it actually has a new idea in it, although there are actually no results at all. And this article kind of just vanished. We published it and it kind of just disappeared, and we didn't know if anyone was reading it or anything. It had something like 3 citations in the next 5 years, and they were all from me. So as far as we could tell, you know, no one sort of picked up on this idea, because perhaps because it was a bit new, a bit crazy, and people didn't know quite how to do it. But that's the basic idea. If you think about it, porous solids, zeolites, MOFs, fantastic selectivity, but they don't flow. On the other hand, you've got liquid solvents. These are ubiquitous in chemistry and chemical engineering. They dissolve things, you know, but they don't tend to have the same sort of selectivity that you get in a porous solid. So you can't imagine a solvent that would dissolve preferentially different isomers of xylene, for example. You may get dissolution based on different polarities and this sort of thing, or an actual chemical reaction, but you can't get size and shape selectivity. So if you could put these two things together, then you've got porous liquids, you've got fluidity, potentially you've got size and shape selective dissolution. And also what I'll show is you actually got massively enhanced dissolution. So just briefly then, there's different sorts of porous liquids, as I'll talk about in a minute, but just this basic idea that in normal liquids, you don't have permanent porosity. What you have is transient porosity just between the molecules as they come. And so that porosity, the pores themselves, the spaces are very small, much smaller than a typical molecule. They're short-lived spaces, and they're not very well defined in terms of shape. So that's a very different sort of porosity to what we're talking about here, where you have large molecular cavities that are well defined. And something I really like about this is this: if you go back to the 1950s and you look at this thing called scaled particle theory, the concept of holes in liquids is there, and it's used as a sort of construction, a way to think about dissolution. So although these pores don't actually exist, scaled particle theory breaks it down and says if a solute dissolves in a liquid, then the first step is that the liquid molecules have to get out of the way and you have to form a cavity. Now, it doesn't literally mean that that happens, but that's one way to think about it. And that turns out to be the biggest energetic cost for a solute to dissolve. So basically, it's solvent molecules having to get apart from each other and make a space. So this is the key thing. If we've made the space already, you've taken away the thermodynamic, barrier, if you like, to dissolution. And that means you get much higher solubilities of gases. So as I say, there's different ways in which you can do this. There are the sort of like, almost like, clever and difficult ways of doing it. We use a combination of organic structures and inorganic. But you could imagine, let's say, you've got in a normal liquid, you've got spaces between the molecules, very difficult to control. If we want permanent cavities that are well defined, then one way to do that is to build spaces inside your molecules. That means you're into quite large hosts, so organic structures that have a space inside. Now, we call those type 1. That's hard to do. Type 2 is a bit easier, where you say, okay, it doesn't have to be only composed of these host structures with a space inside. You could have them as a solution, as long as your solvent molecule is too big to fit inside here, okay? That's the way you keep the empty space. And we made type 2 ones, and I'll give you a quick example now, and then I'll come on to the type 3. So this is a type 2 porous liquid. These sorts of structures you may not be familiar with, but let me just get the principle across. This is an organic host structure that we made. It's a cage. It's rigid. So even when it's empty, this thing just cannot collapse, okay? And there is a space inside it just there. We made this. We dissolve it in a solvent which is too big to fit inside the pore, okay? So this is an unusual solvent. This is actually a crown ether, but it's perfect for what we want to do here. So you take this host, this cage, you dissolve it in the crown ether, you get a clear solution which now has permanent empty spaces in it. This is a porous liquid. Pleased to say this is a picture of Nicola Giuri, Italian postdoc in my group, who was fabulous, and he made this. And that was the moment when he came into my office, showed the vial, and we said almost jokingly to each other, oh, maybe that's a porous liquid. And indeed it was. So molecular modeling, very important. You can use that to support the idea that there are empty spaces. So here we see these red solid shapes. This is where the empty spaces are in our porous liquid, all inside those cages. And then we go on to what can these things do? And we see that they do indeed dissolve very large amounts of gas. So this is methane solubility measurements done by Margarida Costa-Gomez and her student Laura Pisson. And so this is the amount of methane taken up at 3 different temperatures, 30, 40, and 50 degrees. In blue is the control measurement with just the ordinary solvent, no pores, and we get a certain amount of methane taken up. In green is the solubility of methane in the porous liquid. So you can see that it increases by about a factor of 8. Okay, so we get interesting properties here. What are the challenges now? I mean, I'm very interested in the fundamentals of this, but also, is there any chance to seriously think about applications? And I think that we can, if we find a simpler way to do it. We can't rely on all this organic synthesis, but if we take a very simple approach and we say, we're just going to take off the shelf a microporous solid powder, could be a zeolite, could be a MOF, and we're just going to disperse it into a liquid to make a slurry or a suspension, whatever you want to call it. As long as the liquid molecules, these green things here, as long as those are too big to fit into the pores in our particles, and as long as our particles stay dispersed, then effectively what we've got is a porous liquid. So it's now going to be a sort of milky thing. It's not going to be a clear solution, but it's hopefully going to have these interesting gas uptake properties. So these are what we call type 3 porous liquids, and it is in some cases very simple, porous solid plus a liquid. Bearing in mind, liquid has to be bulky, it can't fit inside. Sometimes with additives to help the stability of the dispersion, and you get these milky looking phases. Very easy, very economical to prepare. We've made hundreds of these, all sorts of different liquid phases. You can have cheap things like silicone oils, etc. Porous solids can be MOFs, they can be zeolites, and sometimes you have to work on particle size and all the rest of it to get it stable, but then you have your porous liquid. So let me talk briefly then about CO2. We talked to Shell a few years ago about this concept of porous liquids, and they said, what about taking CO2 out of natural gas sweetening? And actually, of course, CO2 capture has huge applications. We actually went more for the biogas angle, which is similar, but and we chose to compare our porous liquids to physical solvents. These are polyether solvents that are used for CO2 capture. They're physical solvents. They're not fantastic at absorbing large amounts of CO2, but they're easy to regenerate. So they have that advantage over amines because they're just physical solvents. So we thought, can we actually just take these solvents that are already used for CO2 capture? Can we just add in a porous solid and make a dispersion and basically boost the CO2 capture of the solvent? And that's exactly what we did. So it boils down to something very simple. These are the polyethers that are already used for CO2 capture, trade name Genazol or Selexol. This is a zeolite rho, which is known in the literature to have high CO2 capacity and high selectivity to CO2 over methane. And because the pores are very small, these ethers cannot fit inside. So if we disperse this zeolite into this solvent, we've now got something that's sort of milky looking suspension, and it has much higher CO2 capacity than the original liquid does. Showing you some data here. I'm not going to talk about this in too much detail, but essentially we looked at different pressures, different temperatures, imagining a sort of pressure and temperature swing process to deduce what the CO2 capacity was, the working capacity. How much CO2 can you pump in and how much can you get out? And for Genazol, the solvent itself, we came up with 0.63 millimoles of CO2 per gram. And you can see that's roughly doubled in our porous liquid on the right here. So basically it works. Also notice that the dotted lines here, these are the methane uptake, and that stays really low. So we've increased the capacity and the selectivity for CO2. So then going back to David Rooney, with his help, we put together this rig, which is a lab-based rig, which is a sort of continuous flow rig, and it works on a similar principle to the, to the real large-scale solvent extraction systems for taking out CO2. And it works really, really well. So here, these are the data from the continuous flow rig after a single pass of the solvent through. This is the feed gas which is going in. So this is meant to mimic biogas. We have mainly methane, 65%, 35% carbon dioxide. Using Genazol as your solvent to extract out the carbon dioxide, after one pass through the system, the CO2 goes down to 28%. So 35 to 28, that's good, it's working, it's doing its job. But you see what happens with the porous liquid. Now the CO2 content goes down to 11%. So it's much more effective. We also got a techno-economic analysis done on this by some independent consultants. And they said that if you could just change the setup, so you, instead of putting in the industrial solvent, you put in the porous liquid, what difference does that make? They predicted you can get a 23% operational saving for various reasons, different pumping energies, but also you lose less methane in the process because you have a more selective solvent. So next step there is we're going to on-site trials to see if we can do this with real biogas, and we're looking at other opportunities for CO2 capture as well. We've got some quite exciting things going on there. So let me just conclude then. Although porous liquids seem like a very counterintuitive thing, it is entirely possible to get porosity into the liquid state. You can do it in sort of clever ways, intricate ways, or you can just take a very simple approach and disperse porous solids into the right liquid phase. Solubility and selectivity of gases is dramatically enhanced. The type 3 one's very economical to make, and you can basically improve performance of CO2 capture. So this is more like for the porous materials community, but we normally think of porous materials as being these inorganic extended structures, solids by their very nature. More recently, last 2-3 decades, we've seen hybrid metal organic structures come along, and then purely organic, molecular porous materials, but in the solid state. The thing about molecules is that in principle, you can dissolve them or you can melt them. So you can get to the liquid state now. And if you get the design right, you can preserve the porosity into the liquid state and dramatically change the solubility characteristics. So if I could just briefly plug our spin-out company, Porous Liquid Technologies, all of the porous liquid IP that's coming out from Queen's and from the University of Liverpool is now being assigned over to Porous Liquid Technologies to take it forward. And we're engaging with a number of partners, big and small, to see if we can actually implement porous liquids in some sort of separation process. If I could acknowledge just a few people in my group who've done some of the work that I talked about. Nicola Jury is the terrific postdoc who made the type 2 porous liquid, and Bebe Lai are the two who worked mainly on the type 3 porous liquids. And I hope I haven't gone over time. Thank you very much for listening. I'm happy to answer any questions.
Thank you, Stuart. Very, very interesting. I have a number of questions, but I think we can wait till the end of next talk where we have time for discussion. And we can move into the next speaker, who is Colette Larkin, who will be talking about hollow fiber systems for onboard CO2 capture. So, Colette, are you here?
Yes, I'm here. Hopefully you
Hello,
can
Colette.
see me. Hi. Thank you for the introduction, Evangelos. Shall I start sharing my screen?
Yeah, yes, please. So if, Stuart, you can unset your screen now.
I'm not sure how to stop. I'll stop sharing.
Okay, and now, Colette, you should be able to share your screen.
Yeah. Okay, hopefully you can see that.
Yes, yes, we can see the screen. Thank
Great.
you. Please go ahead.
Thank you, and thank you for to the organisers of this UKEM workshop for inviting me. It's a pleasure to speak to you all today. So I'm going to talk to you about hollow fibre-based systems for onboard CO2 capture with the aim to reduce transport emissions. And I'm proud to say that this work is in collaboration with the Torch Research Group at the University of Edinburgh and Repsol SA. So let's start with why do we need to reduce transport CO2 emissions, which I'm sure we're all familiar with. But I thought I'd start and say that in 2019, the transport sector emitted around 24% of global CO2 emissions, making it the biggest contributor behind the provision of electricity and heat. And without adopting any aggressive or sustained mitigation strategies, transport CO2 emissions are projected to increase to double that of 2000 levels. This is due to a growing demand for global mobility and faster transport modes in emerging economies, making the transport sector one of the most difficult sectors to decarbonise. So mitigation strategies that are well practiced and are commercially available, and I think were also discussed earlier in the workshop, that you can improve the engine efficiency, or you can switch to less carbon intensive fuels. However, alone, these strategies are likely to not be enough to reduce transport CO2 emissions to meet net zero targets because of the projection with global car ownership rates and, as I said, the demand for global mobility. So another mitigation strategy that is used by power plants is to implement onboard CO2 carbon capture and storage, CCS. Here, CO2 is removed by a separation process, stored and transported to a permanent storage location. But due to constraints such as space and weight limitations, commercial onboard CCS technology is not yet commercially available. Nevertheless, companies such as Repsol SA, Mitsubishi Heavy Industries Limited and Saudi Aramco are striving to make onboard CCS a reality, particularly in the maritime sector as well, might I add, because the less carbon intensive fuels for that vehicle essentially non-existent or at very low technology readiness levels. So to overcome the size and weight limitations, we need to develop a compact CCS system. Looking at the CO2 capture stage only, one technology that provides a promising solution is the hollow fibre. A hollow fibre is essentially a long, thin tube, which in industry can range from lengths of 1 to 1.6 metres. But what makes a hollow fiber unit special is the high surface area to volume ratios that are generated from its microstructure. So if we take a close look at the cross section of this hollow fiber, we can see it has channels. And I've decided to show you a hollow fiber with 4 channels, as this is what I've been using in my research. But by modifying the fabrication process, you can produce any number of channels. And taking a magnification of the cross section, we can see the morphology of the hollow fiber and the sandwich structure it possesses, consisting of a sponge-like region and a finger-like region. And the finger-like region is what generates this high surface area to volume ratio. These finger-shaped pores represent thousands of open, conically shaped microchannels that are perpendicularly distributed around the empty channels. And since the fingers are open, gas flowing into the hollow fiber channels enters the finger via diffusion with ease, such that pressure drops remain favorably low. And to create a capture system, what you can do is you can take multiple hollow fibers and glue them together to create a module, and this doesn't affect the performance of the individual hollow fiber, so it can make the scaling up of the system very simple and easy. And so now I will say that there are 3 applications as to how you can use the hollow fiber in order to capture CO2 in the exhaust, which I'll briefly introduce now. The first application uses the hollow fiber as a contactor. So in this instance, the fingers of the hollow fiber provide a gas-liquid interface for mass transfer. Here, the material of the hollow fiber can be inert, or it can be coated to enhance the CO2 separation process. And an issue that they often find is with water, causing the pores to no longer be as open and actually wetted. So they're looking into adding a material that inhibits that. The second application is to construct the hollow fiber with a permeselective membrane that is selective to CO2, such that only CO2 passes through the walls of the hollow fiber. So this is using the application is as a hollow fiber membrane, and that's quite common as well. The third application is to use the hollow fiber as an inert support and deposit an adsorbent material into the fingers of the hollow fiber, forming a hollow fiber adsorption unit. Here, the CO2 diffuses into the fingers where it contacts the adsorbent and is captured. And the work that I will present to you today is based upon using this application, and I will discuss that now in more detail. So the work that I have been completing aims to compare the performance of a hollow fiber adsorption unit against that of a packed bed unit to capture CO2 from an exhaust, from a vehicle exhaust, and using an equivalent mass of adsorbent material. And we hypothesize that the hollow fiber adsorption unit will achieve a higher CO2 loading per unit of adsorbent than the packed bed adsorption unit. We also anticipate that the hollow fiber adsorption unit will occupy a lower volume than the packed bed adsorption unit, such that it can be implemented in a vehicle, overcoming size limitations to progress on board CCS technology. And so the agenda for the remainder of the presentation will be for me to discuss the fabrication and characterization of the adsorption units, with a particular focus on the hollow fiber adsorption unit and the reaction conditions that were used and the results and conclusions of the work. These photos are a snapshot of the hollow fiber support fabrication process used to create ceramic hollow fibers and show what the hollow fibers look like. So then the hollow fiber support for the hollow fiber adsorption unit was fabricated by phase inversion, followed by sintering at high temperatures. The phase inversion process takes place during the spinning stage of the hollow fibers and produces a hollow fiber precursor, which can be seen leaving the spinneret. The hollow fiber precursor is then placed into an oven at temperatures of around 1400 degrees Celsius to complete the sintering process, giving the final ceramic hollow fiber support. So for our work, we used alumina hollow. And the remaining photos are of a multi-channel hollow fiber and single-channel hollow fiber that I've just included for your information, so you can see what different variations hollow fibers can look like. So once we have our alumina hollow fiber supports, we can deposit the adsorbent material inside the fingers. And in this work, we selected calcium oxide as the adsorbent material, since it is a cheap and widely researched CO2 capture adsorbent. The Sol-Gel Puccini method was employed to deposit the calcium oxide. And the first step of the method was to make the precursor solution, which was pipetted into the hollow fibre. The outside was covered using Teflon tape to ensure only the inside of the hollow fibre was impregnated. The second step was to let the precursor solution dry in an air atmosphere overnight at 65 degrees. This produced an orange cake. And thirdly, the cake was calcined in an air atmosphere at 900 degrees Celsius for 5 hours. This produced the characteristically white calcium oxide solid and formed the hollow fibre adsorption unit. And the same method was used to create the pellets for the packed bed adsorption unit, except that was all undertaken inside a beaker. But how do we know if one impregnation loop is the most optimum? So to investigate this, we developed 5 hollow fibre adsorption units and tested those, with the number of impregnation loops increasing incrementally with each subsequent unit. And this bar chart shows the amount of calcium oxide deposited per unit length of hollow fibre for the 5 hollow fibre adsorption systems. After 4 and 5 impregnation loops, we can see that the amount deposited has plateaued, indicating that the fingers were likely saturated with calcium oxide. And to get a better understanding of how increasing the number of impregnation loops physically affects the hollow fibre adsorption unit, SEM photos and EDX surface mapping images of the hollow fibre adsorption units after impregnation were obtained at magnifications of 25, 100, and 5,000 of the cross section of the hollow fibre adsorption units. And from the photos, it can be seen that the neat, open, porous structure becomes progressively filled as the number of impregnation loops are increased. And taking an EDX analysis of the hollow fibre adsorption units at a magnification of 100, it can be seen that the calcium atoms are homogeneously distributed and increase in frequency as the number of impregnation loops increased. And then another characterization technique in the form of mercury intrusion porosimetry analysis was conducted, as it shows the empty volume present within the fingers and hence the impact the number of impregnation loops has on the pore size distribution within each of the hollow fibre adsorption units. So as you can see here, we've got pore size distributions for this finger-like region and the sponge-like region that are present within each of the hollow fibre adsorption units. And since we're depositing our calcium oxide in the finger-like region, I will focus mainly on discussing the impact and what the mercury intrusion porosimetry results show. And they show that as the number of impregnation loops increased, the peak pore size diameter and intensity of the pore size distributions for the finger-like region decreased. And if we pair these results with the SEM and EDX images shown previously, we have identified 3 possible deposition scenarios that the 5 hollow fibre adsorption units can be separated into. So after 2 impregnation loops, the pore size distributions are approximately identical to that of the after 1 impregnation loop, suggesting that the calcium oxide deposited didn't fill the fingers nor reduce the opening to the fingers. Therefore, we propose that the hollow fibre adsorption unit 1 and 2 exhibited the particle deposition scenario. After 3 impregnation loops, the pore size distributions of the finger-like region shifted to the left marginally without a decreased intensity of the peak. And this suggested that a thin coating of calcium oxide covered the entire inner surface area of the fingers. Whereas after 4 and 5 impregnation loops, the pore size distribution shifted to the left considerably and decreased in intensity. So this suggested that the inner surface area of the fingers was covered entirely by a layer of calcium oxide that was so thick it filled the fingers. And the finger fill deposition scenario effectively builds upon the thin coating scenario, such that once the inner surface area was completely coated, applying additional impregnation loops resulted in calcium oxide depositing onto the existing calcium oxide layer. And so overall, we can see that as expected, as you increase the number of impregnation loops of calcium oxide into the hollow fibre adsorption unit, you are going to increase the saturation level and fill the fingers. So moving on to the experiment conditions, which are used to test the performance of the adsorption units in terms of their CO2 capture. So the CO2 capture performance of the hollow fibre adsorption units was tested using a feed of 14 volume % CO2 balanced in air at a flow rate of 100 millilitres per minute. at standard temperature and pressure. A concentration of 14 volume percent CO2 was selected as it mimics the concentration of CO2 present in a vehicle exhaust. The reversible reaction that takes place between the solid calcium oxide and gaseous CO2 produces solid calcium carbonate. And to produce stabilized results, 5 adsorption-desorption test cycles were completed for each adsorption unit, and adsorption and desorption temperatures of 650 degrees Celsius and 900 degrees Celsius were selected in accordance with literature. And I've included a schematic here to show how the feed flows through the hollow fibre adsorption unit and how the CO2 diffused into the fingers where it contacts the calcium oxide. And on the right-hand side, you can also see a photo of the hollow fibre reactor where we place the hollow fibre adsorption unit inside. And this reactor is particularly interesting as it allows my group to test very small hollow fibres, which is really useful. So for instance, in my work, the hollow fibre adsorption units were no longer than 10 centimetres. And lastly, we will now look at the results and conclusions of the CO2 adsorption performance testing. So when analysing the performance of the adsorption units, it is important to define a criteria to compare the results against. So in the case of CO2 capture systems, the capacity of the unit is important as this represents how much CO2 can be captured by the system. And so on the graph that I'm showing, you can see that in red, that represents the total capacity per unit length for the 5 hollow fibre adsorption systems. But another important criteria is the purity of the CO2 capture outlet stream. In order to store the CO2 permanently, the CO2 captured should have a high purity. However, achieving high purities typically requires a lot of energy and it's costly. So studies conducted by Pera et al. Discovered that at a purity of 95% CO2, liquefaction costs were reduced. So hence, I've defined an effective capacity as the capacity of the system to achieve an outlet purity of CO2. Although it should be noted that this does result in a portion of the total capacity being lost, which is, what you can see there in red. And looking at the capacity per unit length obtained for each of the hollow fibre adsorption units at the 5th adsorption cycle, you can see that the hollow fibre adsorption unit that obtained the highest capacity per unit length was hollow fibre adsorption unit 3. And this behaviour can be explained by the thin coating of calcium oxide that was deposited inside the fingers of the hollow fibre adsorption unit, which maximised the surface area offered by the alumina hollow fibre support. And so once we then obtained this optimised hollow fibre adsorption unit, we were able to compare it against a packed bed adsorption unit that used an equivalent mass of calcium oxide, and we tested it under the same reaction conditions. A particle size diameter of 150 microns was used for the calcium oxide pellets in the packed bed adsorption unit to minimise mass transfer resistances. And so in this instance, the capacity per unit volume was compared for hollow fibre adsorption unit 3 and the packed bed adsorption unit, as this provides an indication as to which unit can capture the most CO2 whilst occupying a smaller volume. And the effective capacity per unit the effective capacity per unit volume for hollow fibre adsorption unit 3 was 3.3 times greater than the effective capacity per unit volume for the packed bed adsorption unit. And this can be explained by the intensified contact that was achieved between the calcium oxide and carbon dioxide due to the minimised external and internal mass transfer resistances and now residence time distribution that is offered by the morphology of the hollow fibre. And I will discuss this in more detail in the next slide. So to understand why the mass transfer resistances inside the hollow fibre adsorption unit are minimised, computational fluid dynamics simulations using CC+ were undertaken at 5 different volumetric flow rates. And from the simulations, a plot of mass transfer coefficient against volumetric flow rate was obtained, as shown, to assess the external mass transfer limitations of a hollow fibre adsorption unit. And zooming in the grey area, it can be seen that at our feed flow rate of 100 centimetres cubed per minute, the diffusion of CO2 is not externally mass transfer limited. Now, if we look at the internal diffusion limitations, the internal diffusion of a gas into a pore can be described by the effective diffusion, dF, which is related to the bulk diffusion coefficient D, porosity, tortuosity, and constriction factor of the pore bodies, So for the pellets of a packed bed adsorption unit, the internal diffusion of CO2 is limited by a complex network of tortuous interconnecting pathways of pore bodies with varying cross-sectional areas, giving an effective diffusion coefficient that is less than the bulk diffusion coefficient. However, in a hollow fibre adsorption unit, the CO2 flowed through the empty channel before diffusing into the open microchannels of the finger-like region. And as shown by this snapshot of a velocity profile for the flow of CO2 inside the fingers, we can see that, again, we know the CO2 enters the fingers by diffusion only. Thus, for the hollow fibre adsorption unit, the internal diffusion is governed by the opening of the fingers, which possess a porosity, tortuosity, and constriction factor equal to 1. Therefore, for a hollow fibre adsorption unit, the bulk diffusion coefficient is approximately equal to the effective diffusion coefficient. And then looking at residence time distribution, deviations from the ideal flow patterns, such as stagnant regions, typically arise in packed bed systems and cause the performance of the system to be lowered, whereas for a hollow fibre adsorption unit, the residence time distribution should be close to ideal due to the empty channels of the hollow fibre adsorption unit minimizing the possibility of deviation from the ideal flow pattern that typically takes place for the packed bed. And so to conclude, this work provides critical information to advance the design of future hollow fibre-based adsorption units. The thin coating of calcium oxide inside the fingers of the hollow fibre adsorption unit. 3, increase the calcium oxide loading without reducing the surface area available for adsorption. And this demonstrates that the amount of CO2 adsorbent deposited can be optimized to maximize CO2 adsorption whilst reducing the size and cost of the adsorption unit. Additionally, the optimized hollow fibre adsorption unit outperformed a packed bed adsorption unit despite the two units using an equal mass of calcium oxide. And the improved CO2 capture performance of the optimized hollow fibre adsorption unit 3 can be explained by the morphology of the hollow fibre adsorption unit achieving an intensified contact between the CO2 and the calcium oxide due to the minimized mass transfer resistances and narrow residence time distribution. So the results of this work will hopefully underpin the design and development of future hollow fibre-based adsorption systems for onboard CO2 capture and will facilitate a cleaner transition to a carbon neutral fuel sources in the race to net zero. And so now I'd like to finish by thanking everyone who have collaborated and who has supported this work, and this includes those at the University of Edinburgh, Repsol, Imperial College London and Nanjing Tech University. And thank you also to our sponsors, the EP, SRC and Repsol. And thank you all for your attention. I'm happy to answer any questions you may have.
Thank you, Colette, very much. Very interesting, very interesting. So the panel now is open to discussion, and I think we already have a question from Juan for Stuart. And this question says, how did you measure CO2 uptake in your porous liquids?
So we use a sort of modified PAR reactor where we simply measure the mass flow of the gas going in. We evacuate and then we measure the mass flow of the gas going in. That's our normal method for doing it, and we measure it, typically at different pressures and different temperatures, and that seems to work okay.
Okay. I have a question for Stuart, actually, that I will expand to Colette as well, because I see that Colette is trying to work with structures to effectively capture CO2, for example, and I see that, but they work at temperature, and I see Stuart is working with some porous liquids which seem to be able to capture CO2 and among other gases. And I was wondering, can we actually link the two and use these porous liquids infiltrated on the hollow fibers to be able to capture CO2 at room temperature, for example, or very low temperatures? And then I extend the questions about if, Stuart, have you studied the wettability of these porous liquids in different supports? For example, an alumina support, will the porous liquids remain within the porous network, or will just wet everything and go? And then my next question related to that is if actually there is any potential for ion conductivity through the porous liquids, because this we've seen for systems like separation systems that use molten salts as well, that ionic conductivities are very important for chemically selective permeation of CO2.
Okay, it's a lot of questions there. I mean, I suppose I can start and then Colette can ask. But I have to say, I was listening to Colette's talk, and I thought it was very interesting. And I was struggling to think to myself, crikey, how do, is there some way that we combine her technology with the porous liquids? And I think, to be absolutely honest, I don't know enough about I don't understand enough about what Colette's doing to say for certain, but obviously, I mean, one possibility with liquids is you can flow them through pipes. That was the whole idea. So whether there's something in that, being able to flow these liquids through the hollow fibers, but that may be very, very naive on my part. I don't know what Colette thinks.
Yeah, I mean, I must admit, I was thinking the same thing when I was listening to your talk. Oh, could they be combined, particularly perhaps for a hollow fiber membrane contactor? So using the high surface area to volume ratios of the hollow fiber with that porous liquid. But I suppose, yeah, it would be interesting because you do. So with your liquid, do you need to improve the surface area to volume ratio, or in terms of capture performance, because that's what the hollow fiber does in that sense?
Okay. Yeah, I mean, that is something, but which we like to maximize if we can. And if we're talking about these type 3 porous liquids, the obvious way to do that is you basically just go for a higher loading of the porous solid into it, but then you hit problems because you need something, you probably want to keep the viscosity low, as low. So there's a trade-off there. But yes, I think we I don't know how directly this applies to your thing, but one thing that we are looking at is just separating the porous liquid from another phase through membranes, and phase could, for example, even be a liquid. So this is more for sort of extracting something out of the liquid, and because the problem being that with our porous liquids, once you contact them with another liquid, then it all tends to get a bit too complicated, and you can't really separate them afterwards. So we've only just started thinking. Well, we've done some experiments with just with some fairly standard, organic polymer membranes, but we haven't got beyond that to think about how we'd do that with anything more sophisticated.
I was thinking, Stuart, mostly actually infiltrating the porous liquids within the pores of the hollow fiber. So,
okay.
Yeah.
Right. Okay, I'm with you now. So yes. Right. So I think that probably comes. So mostly with the porous liquids, what we've studied has been total uptake. We've not really looked at diffusion, but actually something Nancy and I have been talking about, and this idea that, so you have holes in the liquid, are we able now to act as properly like a sieve and only let certain molecules through? I suspect that there's going to be some sort of effect that way. We haven't managed to sort of quantify that yet. I think that is a whole other issue to start looking at with porous liquids. Very few people have do that, but I agree. I think there's a lot of potential there. And then I guess if I understand the question right, then we're into something where we could load it into the pores of your material and then see a sort of sieving effect. And I guess that relates to the other question that you had there, Vangelos, which was, can you coat onto different, coat these things onto different supports? Yeah, I mean, that's the way we're going. We're talking with Nancy already about that sort of thing.
Yeah, that's very interesting. And I was wondering, Stuart, you make these nice porous liquids, and what happens if you leave it on the vial like for 6 months? Will actually the phases separate, or you need to keep them stirred?
Yeah, so you get all the ranges of behavior you'd expect. It depends very much on what your solid is, and what the liquid is, and what the particle size of the solid is, etc. So we typically look for stability of a few days, because they think to ourselves, well, we're onto something there. But they may come out after a few days. Some of it are stable for weeks. If we keep the particle size very small. Also, you can play with the interactions between the solid and the liquid. If you can improve those, perhaps by adding amphiphiles, surfactant type things that can stick to both of them, that can help to keep them into solution. You can surface modify the solid as well, so you can get a whole range of stabilities. I mean, I would say sometimes they simply just don't disperse at all. You stir, you agitate, and as soon as you stop, it just drops out. So we don't call those things porous liquids, but typically, if that's the case, then you can, if you think you might get interesting properties from that combination, you go to work and try to make it stable.
Yeah.
But
and I was wondering, you said that when they mix with other liquids, then they becomes messy. I was wondering about wastewater treatment, for example. Can you pour it in wastewater and then recover, a clean water afterwards? That would be very interesting.
Yeah, so we started going that way because we were pointed that way by some companies who said that there are actually some really difficult problems with wastewater and things like alcohols, dissolved in water, so for antifreeze and all the rest of it, and it's simply not economically viable to recover those by distillation. So that is an unsolved problem. So we started looking at that, and exactly as you say, so you could have a porous liquid which is based on silicon oil, which is in principle is then immiscible with water, but it also has a dispersed solid into it. And once you stir those things together, it just becomes a horrible sort of emulsion.
Yeah.
That's where we start using these membranes. So if we separate water from the porous liquid with a membrane, so we've got a barrier now, then we can do that sort of separation, and that does work well. We just started doing that sort of thing. It would be lovely if we didn't need to use membranes, but so far that's our approach.
Yeah. So in the chat we have a question from Donato for you, Stuart. Have you tried to convert the adsorbed gas by changing the porous material?
To convert it to something else?
Yes, sorry, I can ask the question myself. Basically, you could, since it's quite porous and you can have quite a good selectivity of the gases, could you have like catalysis happening?
Yes,
on those.
There's someone else here who could probably answer that better than me, I think, Nancy. But yes, in principle, you're right. I think it is
in principle, exactly. We would like to, we can say, study better this concept of try to do basically separation and conversion in one step using this system. So this is an idea that we are trying to develop. Because I think that, in principle, you can select like a type of zeolite for the type of reaction of interest and then do catalysis at the same time of capture.
Yeah.
We will talk about that in the next UKEM maybe.
And have you characterized this porous material? How?
Oh, how? It depends what you're dealing with. So so we have this sort of organic ones, that are solutions, and we use all the usual techniques like NMR, and then we'd have quite a lot of computational modeling. But there's another technique which most people haven't heard of, which is positron annihilation lifetime spectroscopy. So this is used to detect the pores in highly disordered materials, so you can't get crystal structures and all the rest of it. So we use that as well. We have to collaborate with other people to do that. It's quite an exotic technique, so we can't do it all the time. But if you've got the ones that have like a zeolite or a MOF dispersed in a liquid, you've got all the usual sorts of things. You characterize the solid first, and you do your best to characterize the dispersion in terms of gas uptake. We actually do PXRD as well on the dispersion, so we can see both components and check that it's still crystalline and this sort of thing. So a combination of different things.
I want to suggest as well, although it's not my expertise, maybe neutron scattering for diffusion may be a good advice.
Yeah, that's interesting. We have actually done a fair bit of that as well. So nice thing there is that we can see structural changes that happen in the solid upon absorption or inclusion of species. So the neutron scattering helps us to do that. And the other thing, actually, the neutron scattering has revealed, none of this is published yet, is that when we're dealing with the organic porous liquids, which are based on cages, they are so concentrated that actually you only have like 10 solvent molecules for every cage. And so the cages are actually coming together and they're aggregating in these things, because they're so concentrated. So we're seeing in the modeling and in the neutron scattering, we're seeing chains of cages. And this, I think, is really interesting because it means that you've now not just got isolated pores, but maybe effectively channels going through the liquid. And I don't know what we do with that idea, but I think it's really fascinating as to whether gas molecules actually jump from cage to cage, you know, along these chains, and whether you can even control the directions of these chains through some sort of liquid crystal, you know, approach. Then you could even control. If you control the orientation, you can control the direction with which gases may diffuse through a liquid, which I think will be something kind of new. So it's a really interesting idea. Yeah, we started using neutron scattering. I confess, we haven't thought about how we study diffusion that way.
There have been few within the kata who study diffusion or within zeolites.
Within zeolites, okay.
Gases within zeolite. But yeah, so it could be interesting for you since.
Yeah, okay.
Force and diffusion.
For sure, I'll have a look at that. Yeah, that certainly sounds interesting.
Thank you.
We have another question from Tom for Colette. So Tom asks, is the mixing of flows through the hollow fiber important? Presumably some relation between channel width and hollow fiber length.
Yes, so thank you, Tom. I think that's a good question, and it's actually something that I haven't paid close attention to. So there may be someone on the call that could answer better than myself. But I would imagine that there probably is some relationship, particularly because when you flow through the hollow fiber, the boundary layer does develop, and that perhaps can, and so you know there will be different mixing that occurs. And that could then have an effect. But since we are focusing on how the gas diffuses into the fingers, yeah, I guess the boundary layer isn't perhaps an issue there. So yeah, something that I would like to look into more to have a more definitive answer. But yeah, I invite anybody else to comment if they have an idea.
Frank, you're muted. Yeah.
Yeah, I can comment on that one. Basically, yes, there is a relationship, and it's pretty much the same one that you will have in a pipe, and is that the diameter of the hollow fiber, it has divided, the length of your reactor, which is the length of the hollow fiber divided by the diameter of the entrance of your fiber has to be at least higher than 50. When you have that ratio, in theory, you have a good mixing throughout the hollow fiber. Okay, so that will be the reply will be like, if you have a reactor, you will be struggling in the first 10 centimeters, but after the first 10 centimeters, you are totally fine, okay, about the mixing. I have a question for Professor Stuart James. Super interesting topic. I really fascinating. Very nice. I was like you, straightforward thinking, how can I place your porous liquids into my hollow fibers? That was the first thing that I was thinking. And there are a few ways that we can do it. But then I was thinking as well in membranes, and you kind of reply what my thought. I was thinking like the way I see your system is, okay, you have a liquid and then you have like some porous, and in these porous you have some cavities. That's very nice. And now because putting the solids, you manage to have a very well organized porous. But what about the continuity in the porous? So it's like if I'm thinking about a membrane, I need to have like some kind of continuity. And then in the example that you put about the CO2 capture, I think that what is happening there is somehow you have some solubility, diffusion solubility throughout the liquid, and then you are using your solids to do kind of the capturing, or you are absorbing in the solids. Yeah. I don't know if this is correct or not.
Yeah. That is right. So I'm not sure. So what sort of point do we address first there? So I feel like
the continuity. I feel like the
continuity. So
yeah, continuity.
Yeah. So I kind of alluded to this a bit before, where you have these organic ones, where the pores are just, each one is just like an individual organic cage, which is then just dissolved, and we get hints of some sort of continuous, chains of these things just through weak interactions. So I don't know if this helps, but with the other ones, with the type 3 ones, I think what is happening is that, essentially the gas is dissolving into the liquid, at the the interface between the gas and the liquid, and it's obviously then the gas molecules diffuse through the liquid, and then, as you say, they get trapped into the solids. So that then basically allows more gas into the liquid. So I think that that's what's happening. So it becomes a kind of an interesting problem in terms of diffusion, because you've got diffusion through the liquid, you've also got diffusion within the particles. And I think what is probably happening, is that, essentially the particles are soaking up the gas as it goes in, and then as it's released, then, you release the pressure, some of the gas molecules come out, that automatically then, starts to release the gas from the particles.
Mm-hmm. Yeah.
Yeah, in terms of continuity, I suppose, trying to sort of nail this down, in the type 3 ones, I think the continuity is provided by the solvent. Does that make any sense? That basically that's what provides the connection, if you know what I mean.
Yeah, I think that as soon as you have a continuity, you also, what you have as well is selectivity, which may be something that is going to be a bit more difficult in the mechanism of like solution diffusion capturing.
Yeah.
But yeah, it seems amazing topic. I really enjoy your talk. Really,
thank you very
really
much.
Nice.
Yeah.
I'm sure that we can find a way to place this thing in the whole fiber. I'm already thinking, so I will contact you.
Very good. I'm open to ideas. So.
And there is another question from Stuart. Stuart, this is to Stuart. Oh no, sorry, from Adam to Stuart. Sorry. Have you investigated the desorption of the gaseous species from the solid and then the liquid?
The what? The destruction? The
desorption of the gaseous species.
Oh yeah, sorry, I didn't mention about that, but yeah, the desorption is actually pretty straightforward, because these are simply physical sorbents, and so really the type 3 porous liquid, its properties in terms of its bulk uptake and how easy it is to get the gas back out again is it's basically the same as what you would have for the liquid and for the solid individually, so it's really the same, that you release the pressure, increase the temperature, and out comes the gas from the liquid and out comes the gas from the solid. We take CO2, for example. I can't off the top of my head remember what sort of activation conditions we use, but it might be 50 degrees C for half an hour or something like that at reduced pressure, and that takes all the CO2 out. But that's not optimized. It's just sort of proof of principle that you can take the gases out, and you don't need high temperatures to do it. And that's one of the advantages of physical sorbents over amines, where you need very high temperatures to get the CO2 off again.
Yeah. Very good. Amazing stuff. Very interesting. This session I found very interesting. So I would like to thank the speakers, and we will have a break now for 20 minutes. So we will come back in 20 past 1 for the last.
Perfect. And this session is going to have 2 speakers, and the first one is going to be Adolfo Lulianelli, which is coming from the Institute of Membrane Technology of the Italian National Research Council, and is going to be talking about membrane engineering for blue hydrogen generation. So Adolfo, wherever you want to start, the floor is yours. Looking forward for your talk.
Thank you. Thank you for the introduction. I try to share my screen. Do you see my screen?
So far, we cannot see it. So I think that it's coming. Yes, we can see it, but we cannot see it in presentation mode. So maybe you can. Perfect. Now it's perfect.
Okay. Okay. Thank you, and sorry for this delay. Well, first of all, I would like to thank the UK Emission Control Workshop organizer for inviting me to have this speech. Before it was introduced, the title, Membrane Engineering for Blue Hydrogen Generation. So let me start by presenting in brief my research institution. I work in the National Research Council of Italy. It is constituted of more than 100 institutes with more than 7,000 employees. The CNR headquarters is located in Rome. And today I'm working in the Institute of Membrane Technology in the University of Calabria, in the south of Italy, in Cosenza City. We have another subsection in the north of Italy, in Padua City. And in Cosenza, there are 7 institutes, and actually I'm playing the role of representative people of all the personnel of these 7 institutes with more than 200 employees. Well, regarding my research activity, I'm involved in the research of generation of hydrogen separation purification by applying the membrane reactor technology, particularly for producing high-grade hydrogen useful to supply high temperature and low temperature PEM fuel cells in the framework of automotive applications and by exploiting bioresources. In this regard, the past September 1923, I was the chair of the International Conference on Hydrogen Production, which was held under the patronage of the International Association for Hydrogen Energy. And in that occasion, we discussed about many typologies of hydrogen generation, because the produced hydrogen is not the same. In particular, the gray hydrogen is the dominant hydrogen generation modality today, unfortunately, because it is related to the steam reforming process of natural gas as a fossil fuel, producing carbon monoxide and in particular CO2 released in the environment. Then blue hydrogen made using the carbon capture and storage and using derived of biomass, which allows to reduce the greenhouse gases released in the atmosphere. The turquoise hydrogen made using methane pyrolysis, producing solid carbon instead of carbon dioxide. Green hydrogen made using the electrolysis process by renewable energy without any carbon emission. And the pink hydrogen as well produced by electrolysis via nuclear power plants. Well, my research activity is particularly devoted to analyze the impact of membrane engineering in blue hydrogen generation. And looking at this slide, I would like to present to you the IEA report realized during the G20 in Japan 2019 related to the future of hydrogen sizing today opportunities. And in particular, on the left of this slide, it's possible to observe how most of the dedicated production of hydrogen comes from natural gas, so gray hydrogen generation. And on the right, the demand for pure hydrogen coming from refinery, ammonia, transport, and other processes. And in particular, and sorry for the repetition, I'm particularly interested in the demand for pure hydrogen because my research activity is related to the production of high-grade hydrogen through an alternative technology such as the membrane reactors. Here, I would like to show you a qualitative comparison between the gray hydrogen produced in a multi-stage conventional process with respect to an intensified hydrogen production purification membrane-based system. In particular, on the left, the conventional multi-stage process, and the natural gas is fed with steam in a conventional reformer operated at high temperature and high pressure, 700, 900 degrees Celsius, and pressure higher than 20 bar. And the reformer stream or the syngas stream rich in hydrogen comes out from this reformer, and it needs to be further treated in order to purify, to separate and purify the hydrogen present inside. So 2 water gas shift reactors, in particular high temperature, low temperature shift reactors, allow to convert the carbon monoxide present in this stream into further hydrogen and CO2, and then a pressure swing absorption stage allows to separate the CO2 from the hydrogen that now is pure. On the right, it's possible to observe a unique stage process. In this case, it is the membrane reactor in which it's present a membrane, a hydrogen selective membrane, which allows to generate hydrogen and simultaneously separate it as a high-graded stream. And the non-permeated stream called retentate is rich in CO2, and this CO2 is captured or used to produce in a second stage process synthetic fuels. In particular, the membrane housed inside the membrane reactor module allows to remove the hydrogen produced during the steam reforming of derived of biomass such as biogas, bioethanol, biomethanol, and the hydrogen removed from the reaction site for permeation through the membrane is recovered in the permeate side of the membrane reactor module. This allows the so-called shift effect on the reaction systems, because by removing hydrogen from the reaction site, the reaction is shifted towards the products. And this allows to shift also the conventional tire value and to recover as much as possible high-grade hydrogen. Well, in this regard, membrane reactors can be defined as an alternative technology meeting the objectives of the green chemistry and engineering and the sustainability. And this because membrane reactor can allow the reduction of the cost, because the production simultaneous separation, purification of hydrogen is carried out in only one device, and therefore as an intensified process, the cost of several stages are reduced, a reduction of waste, a reduction of non-renewables used both for converting hydrogen, natural gas into hydrogen, because it's possible to use biogas or bioethanol or other derived of biomass, and to avoid the utilization of part of derived of fossil fuels to provide the energy input to the membrane reactor system. And in particular, due to the presence of the membrane inside the membrane reactor module, it's possible to show this graph, this theoretical graph, in which the conversion at the same temperature of a membrane reactor operated at the same condition of an equivalent conventional reactor, the conversion can overcome the thermodynamic equilibrium conversion of the equivalent traditional reactor. And this because a membrane reactor is not a closed system, and therefore it is not limited by the thermodynamic equilibrium conversion. Otherwise, by reaching the same conversion of an equivalent conventional reactor, a membrane reactor can be operated at milder conditions, lower temperature, lower reaction pressure. And this allows to reduce the energy inputs required for realizing the process for generating hydrogen. Now, looking at this graph in which the hydrogen permeability versus the reverse of temperature is plotted for several anorganic membrane materials useful for hydrogen perm-selective membrane preparation, it's possible to observe in the upper part of the graph the metals niobium, vanadium, and tantalum possessing the highest values of hydrogen permeability with respect to the other metals. Furthermore, the permeability of hydrogen for these three metals increases by decreasing the temperature, and this is a fantastic behavior. Unfortunately, for these metals, the hydrogen brittlement phenomenon is the worst effect can happen, and this occurs because when we expose these metals to a long time operation hydrogen permeation test, the membrane can become brittle and then it fails. Therefore, palladium today is the dominant membrane material for separating and purifying hydrogen. Unfortunately, in this case, the permeability of hydrogen for palladium membranes increases by increasing temperature, but it is the highest at the related temperature with respect to other metals. However, also for palladium membranes, the hydrogen brittlement phenomenon can happen. And in this case, it happens below 300 Celsius degree and below 20 bars. Therefore, palladium can be alloyed with other metals such as silver, copper, nickel, ruthenium, gold, and so on. And the permeability of hydrogen of the alloyed palladium-based membrane can overcome also the permeability of hydrogen of the equivalent, the corresponding pure palladium membrane. So today I would like to show you the experimental campaign related to the steam reforming reaction of a synthetic biogas stream to produce high-grade hydrogen, in this case, pure hydrogen, 99.9999% of hydrogen using a palladium, a self-supported palladium silver membrane. It is shown here. The membrane, the tubular membrane is housed inside the membrane reactor module as reported in this schematic. And the catalyst is packed, in this case, in the lumen of the membrane, of the tubular membrane. Here, the picture of the bench scale setup. And here under operation, we use a range of temperature 300, 400 Celsius degree and the reaction pressure up to 3 bar, analyzing the steam to methane feed molar ratio equal to stoichiometric values and under defect of steam at a constant space velocity and using an internal standard gas procedure in order to validate the experimental results. Related to, regarding the performance, this graph on the left, it's possible to observe the conversion of methane as a function of the reaction pressure increase. And in blue color, it's possible to observe the conversion of methane in the membrane reactor at 400 Celsius degree and stoichiometric feed molar ratio condition. The conversion is almost complete, and the higher the pressure, the higher slightly is the conversion of methane. And in general, the increase of pressure determines two opposite effects on the membrane reactor system. The positive one is related to the shift effect, because the higher the reaction pressure, the higher the hydrogen permeation driving force, because more hydrogen is forced to permeate through the membrane. More hydrogen consequently is removed from the reaction side, and the conversion, and the reaction is shifted towards the product with an enhanced conversion. Furthermore, the reduction of CO2 in the lead stream in the membrane reactor was higher than 80%, reaching 90% at 2.5 bar. And this is quite important for generating blue hydrogen because we are removing part of the CO2 in the inlet stream, and then this CO2 is not released in the atmosphere. On the contrary, the opposite effect of the reaction pressure increase is related to the thermodynamic effect. Indeed, the steam reforming of methane is a reaction proceeding towards the products with an increase of the moles number. So the higher the pressure, the lower is the conversion. And this is true for the conventional reactor, where the shift effect is not present, and it's possible to observe how to, at higher pressure, the conversion of methane in the conventional reactor decreases from more than 40% to less than 40%. In the membrane reactor, probably due to the balance of these two effects, the shift effect overcame the thermodynamic effect. Under defect of steam at the same temperature of 400 Celsius degree, it's possible to observe the benefits due to the increase of pressure on the conversion of methane, and also the CO2 emission reduction under defects of steam. Even though at this condition, probably the effect of the increase of pressure and the absence of the sufficient amount of steam determined a decrease of the CO2 emission reduction in the membrane reactor. However, at 2.5 bar, we recovered up to 40% of the total hydrogen produced during the reaction as a high-grade hydrogen stream. In this slide, I would like to show you the conversion of methane in the membrane reactor and the conventional reactor as a function of the feed molar ratio. In this case, it's possible to observe how the membrane reactor better performs than the traditional reactor. The higher the feed molar ratio, of course, the higher the conversion in both cases, because the higher the steam amount, with respect to the methane, the higher is the conversion, but the conversion in the membrane reactor was higher, up to almost 100%. And in one case, we realized also the dry reforming of biogas in the membrane reactor, getting a conversion a bit higher than 2%, and the CO2 emission reduction equal to 30%, and the best one was in the membrane reactor at almost 90%. However, by comparing the membrane reactor with the equivalent traditional reactor, it's possible to observe how the membrane reactor is always the best choice with respect to a conventional reform, and in particular, under a defect of steam, where the increase of pressure determines a great advantage of the membrane reactor with respect to the traditional reactor, both for conversion and CO2 emission reduction. But also in terms of hydrogen yield, the membrane reactor results to be a better choice than a traditional reactor by increasing the feed pressure. Well, in this slide, I would like to show you an integrated membrane-based system to produce blue hydrogen, such as the membrane reformer as a first stage in which the biogas is fed, combined to steam to realize a steam reforming reaction to produce high-grade hydrogen permeation through a palladium-based membrane with the purity higher than 99.99%, and not permeated stream reaching CO2 eventual unconverted methane and carbon monoxide is then treated in a second stage process based on a biopolymeric membrane module in which the CO2 is separated from methane. And in this regard, we developed a particular process for realizing polylactic acid membrane as biopolymeric membranes, which were particularly selective to CO2 versus methane. This is the scheme of the experimental setup and the picture of the real planar membrane module. In this graph, it's possible to observe our results at room temperature, in which the selectivity CO2 versus methane is higher than 200 with respect to a permeability of CO2 through the polymeric PLA membrane, higher than 10 bar. And this is just a proof of how the two-stage process based on membranes is possible and available to produce high-grade hydrogen and capturing CO2 in order to meet the requirements of blue hydrogen generation. Sorry. The ongoing experimental activities related to the blue hydrogen generation by biogas steam reform reaction in membrane reactors is related to the development of these two different membrane systems, in particular a bench scale palladium gold over aluminum membrane reactor, in which the membrane, this one, was developed by Nanjing Tech University in China, and we are developing this experimental campaign in combination with the Chinese colleagues, and as an option, a palladium and supported palladium porous stainless steel membrane realized by the University Rey Juan Carlos of Madrid in Spain. In this case, the support is porous stainless steel instead of the alumina as in the first case, and we hope to get very good results by using also supported membranes. And the future perspective of blue hydrogen generation by exploiting biogas as as source for steam reforming reaction membrane reactors is the integration to renewable energy systems, solar and wind, in order to provide the energy inputs required by the membrane reactor to realize the steam reforming reaction. And in this case, if we will meet the objective of providing the energy input of the membrane reactor, the generated hydrogen will become green hydrogen, because CO2 will be completely fully separated without any emission of CO2 in the atmosphere, also related to the energy input required by the membrane reactor. So I would like to take also the chance to promote the World Hydrogen Energy Conference, which will be held next year, June 26-30 in Istanbul, Turkey. And the chairman of this conference, under the patronage, also in this case, of the International Association for Hydrogen Energy, will be the Professor Ibrahim Dinser. And in particular, in this occasion, I will be the track coordinator of the section Hydrogen Separation and Purification. And therefore, I invite you to attend to this important congress related to the hydrogen energy and hydrogen generation. So I concluded my talk, and I would like to thank you for your kind attention.
Thank you very much for your very nice talk, Adolfo. I totally agree with you. I do like palladium membrane reactors for hydrogen separation, and we will discuss them later on in the discussion. But the last speaker that I would like to introduce in this session is Tom Sturgeson. Sturgeon. Well, I'm very bad with this surname. Sorry, Tom. I apologize in advance. Tom is coming from Cambridge, from Materials, and is going to be talking today about metal organic frameworks and can we use them for NOx separation or capturing. So, Tom, wherever you want, the floor is yours, and very looking forward to seeing your talk.
Hi, thanks, Fran. I've got a feeling I might have to quit and reopen Zoom for my screen sharing to work, but my computer was just asking for various passwords. Is this working?
Yeah, it's working. We can see the presentation.
Brilliant. And I just need to go full screen.
F5.
Has that worked?
Yeah, perfect. Yeah, it's working.
Brilliant. Yeah, I'm not quite used to my surname either. It used to be Scrace. And then I took my wife's surname when we got married, so I'm still getting used to Sturgeon. But lovely to have the opportunity to present, so thank you very much for that. As Fran mentioned, I'm at a company called Immaterial. The talk that we sort of prepared to talk about developing a toolbox, that's really developing the company. So I'll give you a bit of the story about the company and what we do. And then look to focus on some recent work that we've done on NOx filtration. So a quick overview of Immaterial. We're an early stage company spun out from the University of Cambridge in 2015. And that was really based on a discovery of monolithic metal organic frameworks. And I'll touch a bit more on what they are. We've been growing quickly, so the picture that you can see here is already substantially out of date. We're now 15 employees and expecting to be 18 probably by the end of this year or possibly early next year. And we work in quite a wide range of areas, but all on this platform technology around porous materials. So predominantly we're working on applications of cleaning air, around hydrogen supply, CO2 capture, and looking to make cooling processes more efficient. So as I mentioned, the porous material that we work with predominantly are metal organic frameworks, and they've been mentioned earlier, which gives a nice context kind of where they sit in that landscape of porous materials. But just to give a quick overview, these are structured framework structures made up of metal species and organic linkers, which create this lattice structure. And the reason why we're particularly interested in them is because of their tunability. So being able to switch the metal species, switch the organic linkers, as well as some of the exceptional properties that these structures have formed. So the degree of tunability means that there's around 100,000 known metal organic framework structures, which compares to maybe 250 zeolite structures. And as a class of materials, they've achieved things like the largest internal surface area of any porous material. One of the challenges for metal organic frameworks has been getting them into applications, because they typically form as very fine powders. So even though they've been developed for over 30 years, and that's led to this 100,000 structures and growing every month, the fine powders are very difficult to build into the applications that we're interested in. So that's where Immaterial's key piece of technology comes in. And that's this monolithic structure, which I mentioned earlier. And you can see some examples on the left-hand side of what our monoliths look like. So a monolithic metal organic framework is really a macroscopic polycrystalline pellet. So it's all about the control of crystallization when we're producing these metal organic frameworks. And we've done this now with tens of different structures. So as far as we can tell, it's applicable to any metal organic framework. So we believe it works with any of the 100,000 known structures, but we obviously haven't got round to trying all of them yet. And one of the really important things about these pellets is you can get close or even all the way to the crystal density. So a lot of the literature performance, which is, so a lot of the performance parameters which are reported in the literature are relative to some of these crystal densities. But in traditional pelletization techniques, you're often adding binder, or you need to compact them, and that can really destroy the properties of the metal organic frameworks. In contrast, this controlled crystallization process allows us to remove or tune the porosity profile and get to something which is essentially a pure crystalline pellet. And that means that in real world applications, we're seeing up to 4 times the volumetric performance of the native powders. And all of this sort of catalogue of work around monoliths, we've been able to show record-breaking natural gas storage. We work closely with the academic group that we spun out from, and they continue to publish high-profile papers on the topic. And it's allowing us to develop a portfolio of IP and partnerships with other organizations, both other academic research organizations. So we're always interested in working with other research groups, but also companies, because we're obviously sitting in that materials provider position within any given supply chain. So it's really this platform technology, and it's applicable in a lot of different areas. And I gave you some of the broad application areas at the start. And I was going to focus in a bit more on some of our breathable air applications, or specifically some of our NOx removal. So looking at what we've been doing with cleaning the air, the project that I'm going to go into a bit more detail on is this one here around domestic air cleaning. And here we're interested in pollutants such as ammonia, formaldehyde, and NOx. We've also been working with the Ministry of Defense and the US Department of Defense on gas mask filters. So looking at a different set of pollutants or toxins in that case. And we're also doing quite a lot of work on cabin air filtration. So again, slightly different species or pollutants are of interest in different cabins. We're looking at in cars, in planes, and also hopefully one day going into space. So the main point of this slide really, hopefully it gives you a flavor of the breadth of pollutants that we're working with, and that relates back to the breadth of metal organic framework structures that we can work with, so they can really be tuned to show exceptional performance for the target pollutant. But also, so that means that we might be looking at different metal organic frameworks in different air cleaning applications, but then there's a lot of synergy around filter systems and the integrability of our monolith form. And in terms of how we'd typically approach developing one of these monolithic MOFs for a given application, it really starts with a phase of finding the right structure for us to work on, so understand the application requirements. And one of the powerful things that we can do here is because they are well-defined regular structures where you can get crystal structures, we can use molecular simulations to explore that landscape. And at the very least get a good ordering of the different structures that we might be interested in working with. We'll also look at the academic literature and everything else that's out there, and that helps identify our sort of starting point. Once we've done those initial investigations, we really try and narrow down the number of materials that we're working with, and ideally do quick iterative development on those, and really optimize the performance. So whilst we might have identified a sort of parent structure in that first phase, we'll now be looking at really tuning that structure in various ways to optimize the performance. And from there, it's a case of going into prototyping, typically with other industrial partners, and hopefully qualification and through to production. So moving a bit more specifically onto domestic air purification, this is a recent project of work that we've been focused on. In this case, we actually started with looking in the academic literature. There are a number of metal organic frameworks which have been highlighted as of particular interest for NOx removal in the academic literature. So that gave us a place to start, and producing monolithic forms of some of those materials to understand how the performance that's reported in the academic literature translates as it goes into a monolith form. Alongside that, we developed a test rig in-house for looking at this NOx filtration. We were working at 10 ppm, so probably a lower concentration than those that are typically reported in the academic literature, but much higher than ambient levels of NOx that you might be concerned about. Beyond that, we're working at temperatures, pressures, and flow rates that would be typical for the sort of domestic air cleaning fans, which are the intended devices for these materials. We looked at the impact of humidity as well, although we had to do that externally. We couldn't build that into our rig, which was really focused on this quick iterative testing. And we've also worked with some of our customers, so some of those manufacturers of air cleaning fans, to verify our results versus their best available technologies. And alongside that, we've looked to identify next generation materials through simulations, and I'll share a bit of detail on that in a moment, which allows us to access structures which perhaps nobody else has ever looked at in these applications before. So in these, we ran breakthrough tests on these monolithic MOFs in our test rig, and comparing to an activated carbon, which was extracted from a commercially available fan, we matched our monoliths in particle size and distribution to those activated carbons, and you can see here we get around 3 times the capacity under these breakthrough tests with our monolithic MOF, this MOF 2B here. Well, you can see there's also this note here around when we look in the literature, we believe that's around twice the capacity of any activated carbon we can find, but it's much harder to make those comparisons because of all the changes in conditions. But we certainly think that we've got enhanced capacity versus the sort of incumbent technology of activated carbons in this application. That's very important. Possibly even more important is when you look at desorption. So once these materials were saturated, we then just switched to running clean air through, and you can see that the activated carbon quite quickly gives off a reasonable amount of the NOx that it had previously absorbed, and in contrast, that is very much trapped within the metal organic framework. And that's despite the fact that it's been saturated with 3 times the NOx in the first place. Now, one of the other reasons why we're particularly keen to work with metal organic frameworks is because they have these regular structures which can be tuned in a very controlled manner. So MOF 2B, which was the results that I was showing on the previous page, still has a degree of mesoporosity, as sort of indicated by this graphic here. We also worked on forming a fully densified MOF2C, so a variant of the same underlying structure, but just removing all of that mesoporosity. And we find on a gravimetric basis, you get very much the same capacity. But what you can see here with MOF2C is we've changed the kinetics by removing the mesoporosity. So pretty much exactly what you'd expect, but certainly nice to show that experimentally. The reason why that could be particularly interesting in an air filtration application is you can imagine how this would translate to that filter operating over a much longer lifetime. On the sort of flip side, in terms of how these devices work, controlling the kinetics, which I guess traditionally you'd do through particle size and shape, we can still work with those levers, but for any given particle size and shape, we get this additional lever of tuning the porosity profile. So it just gives an added tool in integrating these into actual devices. And that's where we're working with our device partners to understand the different integration sort of concepts that they're really interested in. So for example, that might unlock energy efficiencies in the device and all of those kinds of things which people are interested in every level. Alongside the focus on NOx, we have had a look at how they behave with other pollutants as well. For this MOF2, which is our product code for it, we looked at broadband VOC absorption at realistic parts per billion type concentrations, and we see quite a similar performance to what you would see with an activated carbon. The activated carbon does slightly better on some species, and the MOF does slightly better on others, but overall you're absorbing a similar amount. But possibly of more interest is that this same structure, as well as having good performance with NOx, has very high performance against ammonia. So the multi-pollutant aspect of these materials is something else that we're interested to understand in more detail and could be very valuable in applications as well. Now, in parallel to this breakthrough testing, which we use to iterate on optimizing the materials, we also conducted molecular simulations in collaboration with the University of Cambridge. So this is something that we've done quite regularly, and it works from the Cambridge Structural Database, where these 100,000 structures of MOFs I've mentioned a few times are all held, and then down selecting for those to look at hydrophobic MOFs. So we were keen to for moisture in the air to not impact the performance of the structures that we were going to work with. So down selecting for hydrophobicity was certainly helpful in that. And then the further down selection in matching the porosity to the pollutants that we're interested in. So making sure the pollutants can fit in the pore structures. Then we add in some of the immaterial structures that we've been working with predominantly, and run grand canonical Monte Carlo simulations on that data set against these specific pollutants. So as I mentioned previously, we're particularly interested in ammonia, formaldehyde, and NO2. And here, there's nothing, the spread on the x-axis is just to distribute the points. We've really just plotted those against volumetric capacity. The absolute readings that we get from these simulations on volumetric capacity, we found that sometimes they can be quite well matched to what we get experimentally. Other times they can be a bit off, but the ordering is consistently sort of predictive of the right structures for us to be looking after. So order is probably more important than the absolute capacities of these. The structures highlighted with the white labels are some of those materials that we've been developing as monolithic forms. So you can see again with this kind of multi-pollutant focus, MOF18 is one that performs quite well across all three of these pollutants, and therefore one that we're particularly interested to work on for domestic air cleaning. So just to finish up, areas that we're keen to work on. We know we've got a lot more development to do with these materials for NOx removal and hopefully multi-pollutant removal within a domestic device. I'm particularly interested to understand how these materials start to perform as they go into real world type testing. So simulated environments representative of the real world, and then eventually into people's homes themselves. Metal organic frameworks are inherently a more expensive technology than activated carbons. So we're only really going to have an opportunity if the performance that they offer is truly beneficial to people. And that's an area that we're looking to collaborate with the University of York on. That will flow through to product qualification, and we believe that this could be one of our lead markets. So as I mentioned, Immaterial is an early stage company, and our ambition is to get to material sales, and this is hopefully one of the areas that we'll get there first. We're also interested in looking at other NOx filtration applications, and that's really an area to get into more detail in the coming months and years. And as I mentioned, continuing to develop MOS for multi-pollutant situations, but other also challenging targeted pollutants. So I mentioned previously things like airplane cabins. There, the pollutants of interest are really very specific to that environment. Similarly, you can imagine that for gas masks in defense situations, it's quite specific compounds that they're interested in. Longer term, as a company, we're interested in other form factors, both for metal organic frameworks and other porous materials. So that's an area we intend to continue working on, and adding catalytic functionality will obviously be particularly exciting for these sorts of materials, and MOFs are very well suited to that. So appreciate I've already managed to run a little over time, so that just leaves me to thank the people who actually did the work that I've presented here. So Dr. Robin Babu is the chemist who's done the synthesis of all the monolithic MOFs. Dr. Nick Rice is the engineer who built the test rig and led on that side of things. And Dr. Aurelia Lee, who was at the University of Cambridge when she ran the simulations that you've seen here, but has since been employed by Immaterial. So thank you to all of them for letting me present their work. And thank you to all of you for your attention, and look forward to any questions.
Perfect. Thank you very much, Tom, for your very nice presentation. And I think that now we have about 15-20 minutes to open the floor again and to have some discussion. I would like to ask, the audience, if you have any question. If not, I'm ready to make my questions. But I would like to, first people from the audience.
Maybe Fran, I can ask a first question to Adolfo to the presentation. So I noticed the dimension of the reactor that you have the prototype and you're testing, they are quite small. Do you think that will be likely to think about this solution to have like an onboard hydrogen production, at least for heavy truck transportation?
Well, it is hard to reply to your question because, of course, we are in stage development of membrane reactor, not ready as technology at industrial level. And this is because the membrane is the principal variable which can affect this scale up at industrial scale. I mean, of course, we are developing this technology in several countries all around the world. There are several industries involved in hydrogen generation through membrane reactor technology. But it depends on which each country will pay attention to this kind of technology. I have to do an example. In Japan, the hydrogen is produced by nuclear power plants. Hydrogen needs to be separated from tritium and other similar products which are produced during the nuclear reaction. Well, in Japan, there is probably the largest industry related to membrane reactors, and the name is Tokyo Gas Company. This because the industry related to membrane is strongly linked to the production of energy. So Japan made many efforts to produce hydrogen from nuclear power plant, and also the separation and purification of hydrogen without any carbon dioxide emission in the atmosphere. So that country, for example, invested a lot on this technology, and currently membrane reactors are used not only to treat the hydrogen tritium mixtures at industrial level, but also in residential applications. So the hydrogen is produced, for example, in a building to supply a fuel cell to provide the electricity in the building and recover the heat useful for other management activities in residential applications, I mean. Therefore, it depends on the politic used in each country to think about the potential of this technology. Of course, if I have to reply to your question, is the reply is membrane reactors are not ready yet at industrial scale, but the potential is really high because it depends on the choices of the countries to move from a conventional technology, multi-stage conventional process. The steam reforming of natural gas is in everywhere known to produce hydrogen, but that hydrogen is gray hydrogen, a lot of CO2 emissions in the atmosphere. So we have to reply to this other question, parallel question. Is the world ready to move from the steam reforming of natural gas or fossil fuels to derived of biomass to other technologies? Well, when people will be able to reply to this fundamental question, probably we will have the chance to reply also to your difficult question. But of course, we have to invest on this technology because in the last conference I presented during my speech, there was a great attention on the novelty, on the novel technology related to the membrane engineering, not only for the production, but also for the separation, purification, because today I, of course, for a limited time, presented all of the membrane reactors, but there is a huge number of applications related to membranes, not only anorganic membranes, but also polymeric membranes, which will allow to treat hydrogen-rich streams also at lower temperature. And probably this is the correct route. Thinking about polymeric membranes for separating and purifying the produced hydrogen in order to think in a wider horizon. So my reply is not a reply, but it is another question over your question. So I'm sorry, but I'm not able to reply correctly because there are too many open windows on this task. And of course, I'm a membranologist. Therefore, I should say, okay, this is a ready technology, but to be honest, membrane engineering is ready and the dominant technology only in the salination and the water treatment applications where osmosis by membranes and so on are dominant. We have to pay a lot of attention to this task.
Yeah.
Yes, I know. I was like, obviously, it was like a provoking question, and also I know there are like a few efforts on the Chinese market, for example, in which they are prototyping DME fuel cell for onboard application for heavy trucks. So I'm sure that all these kind of like a new solution are like pushed by at political level. So in which the different countries want to, we can say, promote one solution compared to another one. But yeah, thanks anyway for the answer.
Perfect. I think there are some questions on the chat for Tom. I'm going to read the first one. This is coming from Xuan Jun. Thanks both speakers, very interesting work. I have a question for Tom. For the NOx MOF, do you do regeneration of the material? And how about the lifetime of the material? There is more questions. What kind of NOx concentration you focus on? Mainly 10 ppm as introduced. So Tom, I don't know if you can reply to this question, please.
Yeah, a lot of sort of core topics for where we need to go with understanding the materials. I'll start with the concentration. So the main reason for looking at 10 ppm is looking to go as low as we reasonably could and get results in a sensible time frame. The actual the applications will drive the concentrations we're interested in. So for domestic air cleaning, it's more like 10 to 50 parts per billion rather than 10 ppm. But I know I sort of flew through the slides fairly quickly. You could probably see that it takes several days to get full breakthrough at 10 ppm. So going 3 orders of magnitude lower obviously commits you to a pretty significant experiment at that stage. But in principle, so a lot of the literature reports are looking at 1000 ppm for NOx for metal organic frameworks, and in principle it's sort of right across concentrations that we could be interested in. It really just depends on commercial opportunities from our point of view. Regeneration is a super important topic as well, and again focusing on domestic air cleaning at the moment. What we're more concerned about is making sure that it doesn't regenerate at the conditions that it might be used. So again, the test conditions that we shared were at 23 degrees C, and you can see that essentially no NOx comes off at 23. But obviously it gets hotter than that in houses, particularly in the UK with increasing heat waves and minimal air conditioning. I don't know about others, but my flat got to 38 degrees earlier this year. So you don't really want your air cleaner suddenly pumping out a load of NOx because it's got to 38. So that's our first focus, to make sure it doesn't regenerate at relatively achievable conditions. And kind of linked to lifetime, again, for domestic air cleaning, we want those materials to last around 2 years. So the having enough capacity in the materials to effectively absorb NOx over a 2-year period is really what we're aiming for, rather than any kind of regeneration cycle. So we'd expect people to dispose of their filters at the end of the 2 years. But there's an issue around people not disposing of filters in their devices when they should. So all of those things have to be built in. In other applications, regeneration definitely becomes very important. So looking to regenerate either in situ or ex situ. And one of the things for MOFs, either through optimization or just through the sort of inherent properties of a structure, you tend to get relatively low energy regeneration compared to other porous materials. So I don't know the precise temperature pressure that we can regenerate our current materials at, like where that swing is. But yeah, it's very important for MOFs.
Perfect, thank you very much. There are more questions actually in the chat. This one is coming from Colette. She says, thank you to both speakers. A question again for Tom. What is the running time of the screening simulation for the MOF? Can anyone arrive with a set of parameters and live with the most suitable for their application? Is this something you are looking for commercialize? So I think that some of these maybe you have already replied, but yeah, please, Tom.
Yeah. So, I mean, the length of time for a set of simulations does vary. As a rough ballpark, something like 3 months is probably typical. It can be a bit quicker, it can be a bit slower. It really depends on how many different conditions you're looking to investigate. And it also depends significantly on the compound that you're interested in. So remarkably enough, something like water is very complex to simulate, and that really adds a lot of time to simulations if you're including water in the mix. So that's another motivation for down selecting for hydrophobic moths. And then we make an approximation that we don't have to simulate water in the mix. So very relevant question. It's often a key early stage in us working with other industrial partners, and yeah, we do commercialize that.
Perfect. I actually have one question for Adolfo. I have been working for quite a long time with membranes and membrane reactors, especially with palladium-based membranes. And I think that one of the problems of these reactors is always like the price of the membrane. And I don't know, probably we are working with palladium because we want to work at high temperature and we want to have a very high selectivity, I mean, extra pure hydrogen. But maybe you mentioned polymeric membranes, and maybe there are other applications, and that's my feeling, that they don't need such a high purity hydrogen. I don't know, and we can compromise a little bit and we can have the benefit of the price. So I don't know if you want, I'm sure that you have much more experience than me. So if you can comment on these things.
You are perfectly right, because the price of the membrane is, before I was speaking about the main reason why membrane reactors are and not at industrial level in many countries all around the world, and the price of the membrane is one of the variable affecting this development. So I agree, I fully agree with you. And of course, during my presentation, I did not have a chance to discuss about the development of the membrane and membrane materials to contrast the price of the membrane itself. Indeed, in the end of my presentation, I spoke about two different supported membrane applications. In what I presented today, I spoke about a self-supported palladium silver membrane, quite thick, 150 micrometers. Of course, able to separate with a high purity hydrogen, but really difficult to scale up, really difficult to propose for the high cost of palladium. Therefore, now there are two routes to contrast this drawback. First of all, to decrease the amount of palladium, several membrane development are possible. For example, using a ceramic or porous stainless steel support in order to deposit a thin layer of palladium. So I'm working with membranes in which the selective layer is around 5 micrometers. So this could be an option for the future, because if you decrease the amount of palladium inside the kind of membrane, you can decrease the cost, you can propose it at a larger scale, and the general cost of the technology could be available at a larger scale. Second route, we should change the material. So the material, the polymeric material, and I fully agree with you, are available at a cheaper level. Therefore, polymeric membrane materials are quite useful to separate and purify hydrogen. But we are discussing about the generation of hydrogen, and in this regard, polymeric membrane materials are unuseful for generating hydrogen due to the higher temperature needed for whatever reforming process. Therefore, polymeric membranes are a really good solution for separating and purifying hydrogen, but for membrane reactor technology, I do not see at the moment polymeric membranes really available to substitute the inorganic membranes applications. Just to add a few details regarding also the question of Nancy, In Italy, for example, there is a quite important industry which is developing the membrane reactors technology at industrial level and pre-industrial level. The name is KT technology in the middle part of Italy. So they are joined with many huge companies for energy production, in particular hydrogen energy production, such as ENGIE, Total, Snam, Eni, and many others. And US is the dominant country developing membrane reactors applications for energy production, in particular hydrogen energy production. So I believe that the route is this one, to develop really good membrane materials for separating hydrogen, also able to work at higher temperature. For example, one of the new material under development is the graphene. Graphene is full hydrogen selective. Graphene is not so expensive. Graphene needs to be treated to be used as a membrane, because you have to destroy the molecular structure of graphene in order to allow the hydrogen to pass through. This is a kind of different approach, but the research is useful for developing good solution, and we are fighting for that.
Yeah, thank you very much. I do agree. Graphene looks like very promising for membranes. I don't know if there are any more questions on the floor. If no, I think that we have like 20 minutes discussion so far. This is the third session. I think it's been like a very nice day. And I think that we are ready to start like closing the fifth UKEM. I want to say like just 1 minute. I have write down here in my notebook because I was thinking about this. I'm pretty sure that then Nancy will say some words and probably Angelis as well, but I just want to say thank you to all of you. The UKEM started in 2017, okay, and that was very nice, and that was in Edinburgh, and it was after this conference, after this workshop, we went to a pub, Nancy and myself, and we were so excited about like how beautiful it was to meet all these colleagues that we decided to do another one, and then another one, and now we are in the fifth one. Vangelis joined us last year, and this year is here again, and next year we will do it again, and hopefully we will see you in person. Okay, it's been 2 years in a row online, and I just want to say thank you. I'm always saying the same. It's a pleasure to see so many friends together here talking about science. That really makes me so happy, honestly. So thank you very much.
Thank you, Fran. So I think that this brings us to an end. I would like to thank all the speakers of this edition of UKEM. I'm really happy that we were able to do also this after 5 years, and I'm so happy that every time we are like broadening our interest around like clean technology for transport and involve more and more like friends in the UKEM community. So I'm really happy about that. Before closing, obviously, I would like to thank who made that possible. So thanks for the Catalysis Hub for the support along these years, and in